Good evening, dear friend, and welcome back to this hushed corner of the universe we call the Sleepy Professor. You've found your way here again, perhaps after a long day when the world felt too quick, too bright, too demanding. Here, time moves differently. Here, we let curiosity unfold as slowly as morning mist, and we explore the wonders of our world at the pace of a gentle lullaby. Tonight, settle yourself somewhere comfortable, perhaps curled beneath your favorite blanket or sinking into that chair that knows the shape of your tiredness. Let your shoulders drop just a little. Let your breathing find its own unhurried rhythm. Tonight, we're going on a journey that requires no hurry at all, for we're traveling into deep time itself, where a million years passes like the turning of a single page. You might notice the soft light around you. Maybe it's the glow of a bedside lamp, or perhaps the last pale threads of evening light filtering through your window. Wherever you are in the world, whatever corner of night cradles you now, you're part of a quiet community scattered across the globe, each of us listening in our own small sanctuary, yet joined together by the same sleepy story. In Tokyo, perhaps someone is drifting toward dreams. In London, another soul might be finding comfort in these gentle words. In Sao Paulo, another weary mind might be letting go of the day's concerns. We are all connected, not just by this story, but by something deeper. We all rest upon the same wandering earth. If these slow explorations bring you peace, a gentle touch of that like button helps this drowsy channel find others who need the same quiet refuge. If you've already joined our sleepy community by subscribing, your presence here fills me with the warmest gratitude. And if you're new to these gentle journeys into science, you're invited to stay to make yourself at home in this unhurried space where learning happens at the speed of a sleepy sigh. Now, a gentle warning, dear listener. I hope tonight's story helps guide you toward the softest dreams. But if it happens to keep you awake with wonder, at least you'll carry new knowledge with you into tomorrow's light. So let the outside world grow dim and distant. Let your muscles release their hold on the day's tension. Let your mind settle like sediment slowly drifting to the bottom of a still, deep lake. Our story is beginning. Have you ever wondered, as you lie in bed at night, what secret movements are stirring in the darkness far beneath you? The ground feels so solid, so dependable, so permanent. Your bed rests on a floor, the floor on foundations, the foundations on soil, the soil on bedrock that seems to stretch down forever. But all of that apparent solidity is in truth just the thinnest skin on something infinitely more restless. The earth beneath us is not a solid, unchanging ball of rock. It is a dreaming planet, and in its dreams, continents wander like sleepwalkers across its surface. Mountains rise with the patience of growing trees. Oceans open and close like the petals of flowers that bloom across geological seasons. The very ground we trust is always, always in motion, drifting, shifting, dancing to rhythms so slow and deep that they measure time in the rise and fall of species, in the birth and death of seas. Tonight, we'll explore this hidden restlessness together. We'll discover how our planet's surface is divided into great pieces, tectonic plates that float and drift on currents of molten rock. We'll learn how mountains are born from the gentle collision of continents, how oceans spread wider each year, how the familiar map of our world is just one moment in an endless patient dance of stone and fire. But we'll take our time. We'll let each idea settle before moving to the next, like stepping stones across a quiet stream. We'll pause where wonder stirs, linger where imagination finds comfort, because the story of plate tectonics is not urgent. It has been unfolding for billions of years, and it will continue long after our own small dreams have faded into the great dreaming of the earth itself. So close your eyes if you wish, or let them rest half open in the gentle light. Let your breathing deepen. Feel yourself sinking, not just into comfort, but into deep time itself, where the earth reveals its most intimate secrets. Even in stillness, even in the quietest night, Our world is alive with the slowest, most beautiful motion imaginable. In the beginning minds, a world born from fire and patience. Long, long ago, so long ago that the very idea of long loses all meaning, there was no solid ground to rest upon, no mountains to climb, no valleys to shelter in, no gentle hills to roll across in summer grass. There was only fire and chaos and a young planet learning how to dream. Close your eyes and try to imagine it. This infant Earth spinning slowly in the darkness of space. Picture a world glowing like an ember in a fireplace, red and orange and molten, so hot that rock itself flowed like honey. This was not the gentle warmth of a sunny afternoon, or even the heat of a summer's day. This was heat that could melt mountains, heat that made the very air shimmer and dance, heat that rose from every surface in waves you could see. The Earth was 4.5 billion years young then, barely born from the swirling clouds of dust and gas that surrounded our newborn sun, and it was not alone in its fiery youth. All around it, space was crowded with wanderers, asteroids tumbling end over end, chunks of ice and rock left over from the solar system's violent birth. They fell upon the Earth in endless storms, some no bigger than pebbles, others the size of mountains, each one adding its own small fury to the planet's growing fire. Every impact was a hammer blow against the surface, releasing energy that kept the world molten and bright. There was no day or night as we know it, for the sky was thick with the glow of falling stones and rising steam. There was no weather, no seasons, no gentle rains, only the endless percussion of creation, the cosmic drumbeat of a world being born. But even in this apparent chaos, patterns were emerging with the patience that only the universe knows. The heaviest elements, iron and nickel, sank slowly toward the center, gathering into the dense hot core that still beats like a heart at our planet's center. The lighter rocks rose upward, beginning to form the first tentative crusts, though these were fragile things, constantly broken and reformed by the continuing bombardment from space. Beneath these temporary crusts, something wonderful was happening. The rock was so hot, so fluid, that it moved like a thick, dreamy ocean. Currents stirred within it, warm sections rising like bubbles in honey, while cooler areas sank back down. This was the beginning of convection, the great slow circulation that even now drives the movement of continents and the opening of oceans. Even in its molten youth, the Earth was learning how to dance. As millions of years passed, time spans so vast that they make human history seem like the flutter of an eyelash, the bombardment from space gradually eased. The largest wanderers had either crashed into planets or been flung out into the cold reaches of the solar system. The Earth, now larger and more stable, began its first tentative experiments with coolness. In the upper reaches of the planet's thick atmosphere, strange clouds began to form. These were not the white, fluffy clouds we know, but dense, toxic veils of carbon dioxide and methane, sulfur compounds and ammonia, the breath of countless volcanoes mixed with gases released by impacting comets. The sky was dark, lit only by the red glow of lava and the sudden, brilliant flashes of lightning that danced from cloud to cloud. But something magical was happening in those alien clouds. As the surface began to cool, water vapor rose from the dying lava, condensed in the cooler upper atmosphere, and began to fall back down as rain. Not gentle showers, but torrential downpours that hissed and steamed when they struck the hot rock, only to rise again as vapor and fall once more. This cycle continued for thousands, perhaps millions of years, an endless conversation between fire and water that slowly began to tip toward the gentle dominance of the seas. The first oceans were born not from the melting of ice caps or the overflow of rivers, but from this patient dialogue between the planet's fire and the water-bearing comets that continued to visit from the outer reaches of the solar system. Each comet that struck added its gift of ice to the growing pools. Each volcanic eruption released more water vapor into the thickening atmosphere, Gradually, inevitably, the balance shifted. Where once there had been only molten rock and toxic gas, now there were pools, then lakes, then shallow seas spreading across the cooling surface. The water was not the clear blue of modern oceans, but a murky, chemical-rich soup, tinted by dissolved minerals and organic compounds that would someday spark the first tentative experiments with life. And still, the planet was learning to move. The first continents were not the familiar shapes we know from maps, but tiny fragments of lighter rock that floated like rafts on the heavier, darker crust beneath. These proto-continents drifted and collided, merged and split apart in a dance that had no choreographer but heat and gravity, no music but the deep, slow currents of the mantle below. Already, even in these earliest times, the seeds of plate tectonics were being planted. The Earth's crust was thin and mobile, easily cracked by the pressure of rising magma or the gradual cooling and contraction of the surface. Wherever cracks appeared, new rock flowed up to fill them, creating the first spreading centers, where sections of crust collided. One would sometimes dive beneath the other, beginning the long cycle of destruction and renewal that continues to this day. The young Earth was a place of extremes, scorching heat and sudden cooling, violent storms and eerie calms, toxic atmosphere, and life-giving water all mixed together in a cosmic experiment whose outcome was far from certain. Mars, our red neighbor, had faced similar conditions but had grown cold and still. Venus had become a hellish furnace wrapped in crushing clouds. Only Earth found the delicate balance that would allow it to remain forever restless, forever changing, forever alive. Even the moon played its part in this ancient story. Born from a colossal collision with a Mars-sized body, it hung much closer to Earth then, looming huge and bright in the alien sky. Its powerful gravity stirred the early oceans into massive tides that may have helped concentrate the organic compounds that would eventually spark life. It also helped stabilize Earth's rotation, preventing the chaotic wobbling that might have made our planet uninhabitable. As you lie in your comfortable bed tonight, surrounded by the familiar sounds of the modern world, it's almost impossible to imagine the ancient time when our planet was so young, so violent, so utterly unlike the home we know. Yet without that fiery beginning, without those millions of years of patient cooling and settling, there would be no solid ground for us to build upon, no oceans for rain to fill, no atmosphere for us to breathe. The story of that young Earth is still written in the rocks beneath our feet. Every granite boulder, every grain of sand, every pebble you might skip across a pond carries within it the memory of that ancient fire. The very atoms in your body were forged in the nuclear furnaces of stars and scattered across space by stellar explosions, then gathered together in that cosmic dance that formed our solar system. But perhaps most remarkable of all is this: the restlessness that characterized the young Earth has never ceased. The same forces that shaped our planet's violent youth continue to work today, though at a pace so gentle that we can live our entire lives without noticing their quiet persistence. The mantle still churns with slow convection currents. The crust still cracks and heals. Continents still drift across the surface at the speed of growing fingernails. In a sense, the Earth is still young, still growing, still experimenting with new configurations of land and sea. The mountains we think of as eternal are temporary wrinkles in the planet's skin. The oceans we consider permanent fixtures are just the current arrangement of water in basins that open and close like breathing. Even the familiar outlines of the continents are just one frame in an endless movie of geological change. So as you drift towards sleep tonight, remember that you are resting on a planet that has never learned to rest. Beneath your dreams, the Earth continues its own deeper dreaming, reshaping itself grain by grain, year by year, eon by eon. You are cradled by a world that is ancient beyond imagination, yet eternally, peacefully young. The great puzzle revealed Earth's restless jigsaw. Imagine, if you will, that the Earth is not the solid, unchanging sphere it appears to be, but rather like a vast, three-dimensional jigsaw puzzle, one that has been gently shaken and scattered, its pieces drifting slowly, eternally, never quite fitting together perfectly, never quite coming to rest. This is perhaps the most beautiful way to think of our planet's surface, not as fixed continents and permanent oceans, but as a collection of enormous patient puzzle pieces floating on a sea of molten rock, each one carrying its precious cargo of mountains, forests, deserts, and seas. As you settle deeper into your evening's rest, let your mind drift over this planetary puzzle. Unlike the thousand-piece jigsaw you might work on during a quiet Sunday afternoon, Earth's puzzle has no box top to guide us, no final image to complete. It is a puzzle that rearranges itself, whose pieces grow larger and smaller, split apart and merge together in a cosmic game of patience that has been playing for billions of years. The pieces of this puzzle are called tectonic plates, and they are far grander than anything human hands could ever assemble. 7 great plates dominate the game, each one a titan of stone carrying entire continents on its back. Picture them now, these gentle giants of geology, drifting across the planet's surface with all the urgency of a sleepy Sunday morning. The Pacific Plate is perhaps the mightiest of all, stretching across nearly a third of our planet's surface. It cradles the deep blue expanse of the Pacific Ocean in its stone arms, a single piece of crust so vast that you could fit all the continents upon it, and still have room for more seas. Along its edges, like a rim of fire, volcanoes stand in patient rows, breathing warmth into the night sky, reminding us that even the most peaceful-looking places are alive with hidden energy. To the east lies the North American plate, carrying not just the familiar outline of the continent, but also a vast underwater realm stretching halfway across the Atlantic Ocean. It moves westward with the pace of a leisurely stroll, just a few centimeters each year, slower than the growth of your hair, gentler than the accumulation of dust on a windowsill. Yet over millions of years, this patient movement has carried forests and prairies, rivers and mountains across thousands of kilometers of the planet's surface. Below it drifts the South American plate, like a great stone raft carrying the Amazon rainforest, the Andes Mountains, and the rolling pampas across the Earth's curved surface. It presses westward into the Pacific, its edge diving beneath the oceanic plate, in a process so gradual that the mountains it builds, those towering Andean peaks, rise at a rate measured in millimeters per year, like the imperceptibly slow growth of fingernails. Across the Atlantic, the Eurasian plate stretches like a vast blanket from the shores of Western Europe all the way to the far reaches of Siberia. It is the largest of all the continental plates, carrying the history of human civilization on its back. The forests where our ancestors learned to walk upright, the valleys where agriculture was born, the plains across which cultures spread and mingled like streams finding their way to the sea. The African plate, ancient and patient, holds deserts that shimmer with heat mirages and savannas, where elephants walk in the footsteps of their ancestors. It pushes slowly northward into Europe, closing the Mediterranean Sea grain by grain, year by year, promising that someday, in some unimaginably distant future, Italy and North Africa will meet in a gentle collision that will birth new mountains to scrape the sky. Far to the south, the Antarctic plate spins in icy solitude, wrapped in its white blanket of ice, circling the bottom of the world like a great frozen carousel. Around its edges, hidden beneath the Southern Ocean, spreading centers quietly add new stone to its borders, making it larger each year, though so slowly that even the patient penguins that waddle across its surface never notice the change. And then there is the Indo-Australian plate, or perhaps 2 plates. The experts still debate this sleepily, like scholars discussing a point of ancient history over evening tea. The Indian portion continues its ancient northward journey, pushing into Asia with such persistent gentleness that it lifts the Himalayas higher each year, adding a few millimeters to Everest's height as regularly as seasons change. The Australian portion carries its cargo of red deserts and coral reefs northward too, inching toward Asia like a continent-sized tortoise crossing an ocean of stone. But the grand puzzle is far more complex than these seven great pieces. Around their edges, caught between them like fragments of glass in a slowly shifting kaleidoscope, dozens of smaller plates dance their own quiet dance. The Nazca Plate, off the coast of South America, slides beneath its continental neighbor with the patience of water seeping into soil. The Philippine Sea Plate orchestrates the complex ballet of island arcs and volcanic chains that dot the western Pacific. The Caribbean Plate carries its necklace of tropical islands like a slow-moving ship laden with emeralds. Each plate, large or small, moves to its own rhythm, yet all are connected in the great global dance. None can shift without affecting its neighbors. When the Pacific Plate pushes against South America, the Andes grow taller. When Africa presses into Europe, the Alps continue their ancient climb toward heaven. When the Indo-Australian Plate nudges against the Eurasian, the Himalayas reach higher into the thin, cold air. The boundaries where these plates meet are the most fascinating parts of the puzzle. They are not neat, straight lines like the edges of cardboard puzzle pieces, but complex zones of interaction that can stretch for hundreds of kilometers. Some boundaries are places where plates pull apart, like hands slowly releasing their grip on each other. Others are places where plates press together, like lovers embracing. Still others are places where plates slide past each other, like dancers in a slow, eternal waltz. At divergent boundaries, where plates separate, new crust is born. The most magnificent example lies hidden beneath the Atlantic Ocean, the Mid-Atlantic Ridge, a mountain range longer than any on land, running from the Arctic to the Antarctic, like the seam where the planet is slowly, patiently opening itself to make room for new dreams. Here, molten rock rises from the depths, cools in the crushing darkness of the deep ocean, and hardens into new seafloor. Europe and Africa drift eastward, while the Americas float westward, and the Atlantic grows wider by a few centimeters each year. At convergent boundaries where plates come together, the drama is more intense but no less patient. Sometimes one plate, usually the denser oceanic crust, politely dives beneath its neighbor in a process called subduction. It's as if the planet is constantly, slowly swallowing its own skin, digesting the older parts of its surface to make room for the new. These subduction zones create the deepest trenches in the oceans, valleys so profound that they could swallow the tallest mountains and still have room for more. They also create chains of volcanoes as the subducted crust melts and rises again in a different form. When two continental plates meet, neither wants to dive beneath the other. Instead, they crumple together like blankets pushed from both ends, raising mountain ranges that pierce the sky. The Himalayas are still rising from such an embrace, growing taller as India continues its slow, inexorable push into Asia. At transform boundaries, plates slide past each other horizontally, storing up tension for decades or centuries before releasing it in earthquakes. The San Andreas Fault in California is perhaps the most famous example, a zone where the Pacific Plate inches northwestward past the North American Plate, carrying Los Angeles slowly but inevitably towards San Francisco. Each type of boundary tells its own story, creates its own landscapes, shapes its own piece of the great global puzzle, yet all are part of the same system, the same slow, patient dance of creation and destruction, growth and renewal that has been reshaping our planet for billions of years. The puzzle is never complete, never at rest. It is a living thing constantly rearranging itself, growing and shrinking, breaking apart and coming together. Pieces split into smaller fragments. Small pieces merge into larger ones. The very shapes of the pieces change as they move like clouds shifting in a gentle breeze. And we, tiny as we are, live our lives balanced on the backs of these gentle giants, usually unaware of their patient motion beneath our feet. We build cities on their surfaces, plant crops in their soil, sleep peacefully in their embrace, trusting that the ground will be there when we wake, and it will be, perhaps shifted by a few millimeters, perhaps rearranged by microscopic amounts, but essentially the same, carrying us forward on our shared journey through space and time. The great puzzle of plate tectonics is one of the most elegant discoveries in the history of science. It explains why similar fossils are found on opposite sides of oceans, why the edges of continents seem to fit together like pieces of a jigsaw puzzle, why earthquakes and volcanoes cluster along certain lines, why mountain ranges rise where they do. It unifies geology, connecting what once seemed like separate phenomena into a single beautiful story of planetary motion. As you lie in the quiet of evening, perhaps you can feel it, the almost imperceptible drift of the plate beneath you, carrying you eastward or westward, northward or southward, on a journey that began long before your birth and will continue long after your great-great-grandchildren have become part of the patient Earth themselves. You are not just lying still in bed, you are riding through space on the back of a stone giant, part of the grandest, slowest, most beautiful puzzle ever assembled. The deep sleep beneath, the mantle's dreaming heart. Now let your imagination sink even deeper, past the puzzle pieces of the crust, past the solid ground that seems so permanent, down, down into the Earth's most hidden sanctuary. Close your eyes and feel yourself falling gently through layers of increasing warmth and pressure, past caverns where no light has ever shone, past crystals that grew in darkness over millions of years, past the deepest wells ever drilled by human hands, until finally you arrive at the true heart of our planet's gentle motion, the mantle, Earth's dreaming, flowing middle layer. If the crust is our planet's skin, thin and relatively brittle, then the mantle is its flesh and blood, making up more than 80% of Earth's volume. It stretches nearly 3,000 kilometers downward, from just beneath the crust to the edge of the molten core itself. To put that distance in perspective, if you could drill straight down through the mantle, you would travel farther than the distance from New York to Denver, except that you would be journeying not across the surface of the Earth, but through its very heart. Here, in this vast middle realm, the familiar rules of our surface world no longer apply. Rock behaves not like the brittle stone you might skip across a pond or stack into a wall, but like the thickest honey, the slowest taffy, the most patient putty ever imagined, under pressures thousands of times greater than anything we experience at the surface, and at temperatures hot enough to melt copper. The solid rock of the mantle flows and deforms and moves with a liquid grace that would seem magical if we could somehow witness it with our own eyes. The temperature down here ranges from about 1,300 degrees Celsius, just beneath the crust, to nearly 4,000 degrees at the core boundary. Heat so intense it would vaporize any substance from our familiar world in an instant. Yet somehow, the enormous pressure keeps the mantle rock solid, or rather, solid in a new way that has no equivalent in our daily experience. It is solid like glacial ice is solid, maintaining its form over short timescales, yet flowing inexorably over longer ones. This flowing is so slow it makes glaciers seem hasty by comparison. The mantle rock moves at rates measured in centimeters per year, sometimes even less. A drop of mantle material might take 100 million years to complete a single journey from the deep interior to just beneath the crust and back down again. It is motion at the speed of continents, at the pace of evolution, at the rhythm of deep time itself. Yet this seemingly glacial movement is the engine that drives everything we see on the surface. Just as invisible breezes move the clouds across the sky, the patient circulation of the mantle moves the continents across the face of the Earth. The process is called convection, the same principle that causes hot air to rise from a radiator, or steam to curl upward from your morning coffee, but played out on a planetary scale and stretched across geological time. Deep in the mantle, near the boundary with the core, rock heated by the Earth's internal furnace becomes slightly less dense than the cooler rock above it. Like a hot air balloon filled with warm air, this heated rock begins to rise, ascending through the mantle at the stately pace of growing fingernails. As it rises, it cools slightly and spreads outward, flowing beneath the crust like invisible rivers of stone. Meanwhile, at the surface, other portions of mantle rock have cooled and become denser. These cooler regions sink downward through the mantle like gentle waterfalls flowing in reverse, carrying with them any pieces of crust that might be dense enough to make the journey. This descending rock eventually reaches the deep mantle, where it is heated once again, and the great slow cycle continues. Picture it as the planet's own breathing, an inhalation and exhalation that takes not seconds but eons, not air but molten rock, not lungs but the entire sphere of the Earth itself. It is the deepest, slowest breath imaginable, and we live our entire lives balanced on the surface of this breathing planet, usually unaware of the vast circulation happening miles beneath our feet. This convection creates currents in the mantle, streams of flowing rock that meander and eddy like rivers in the sky. Some currents are broad and gentle, carrying continents slowly across the planet's surface. Others are narrow and focused, creating hotspots where plumes of especially hot rock rise from the deep interior all the way to the surface. The Hawaiian Islands are born from one such hotspot, a persistent upwelling of hot mantle rock that has been burning its way through the Pacific Plate like a slow-motion blowtorch. As the plate moves northwestward over this stationary hotspot, new volcanoes are created, one after another, forming a chain of islands that traces the plate's movement across the Pacific. Each island represents a moment when the hotspot punched through to the surface, creating new land where none existed before. Iceland sits atop another such hotspot, this one coinciding with the mid-Atlantic ridge where Europe and America are slowly pulling apart. Here, the combination of diverging plates and rising mantle plume creates an island that is literally growing larger each year as new lava flows harden into new coastline. Iceland is one of the few places on Earth where you can actually watch new land being born. The mantle's deep dreams made visible in flows of molten rock and clouds of steam. But most of the mantle's work happens in darkness and silence, far from human eyes. The great convection cells that drive plate tectonics operate on a scale too vast and too slow for us to perceive directly. We can only infer their presence from their effects. The slow drift of continents, the opening and closing of ocean basins, the rise of mountain ranges over millions of years. Scientists have found ways to peer into this hidden realm, using seismic waves vibrations from earthquakes that travel through the Earth's interior like sound waves through water. By studying how these waves speed up, slow down, and bend as they pass through different regions of the mantle, researchers have been able to create something like a CT scan of the planet's interior. These seismic images reveal a mantle that is far from uniform. There are regions where the rock is hotter and less dense, appearing as slow zones where seismic waves crawl at reduced speed. There are regions where ancient, cold slabs of oceanic crust have sunk deep into the mantle, creating fast zones where waves zip through more quickly. The mantle has its own weather patterns, its own currents and eddies, its own slow storms that rage for millions of years. Some of these ancient slabs may have been sinking for hundreds of millions of years, carrying with them minerals and chemicals from the Earth's surface, slowly mixing the composition of the deep interior. They're like messages in bottles carrying news from the surface world down to the planet's deepest places, ensuring that the mantle and crust remain in chemical communication across the vast gulf of distance that separates them. Near the core mantle boundary, nearly 3,000 kilometers beneath your feet, strange things happen. The pressure is so intense that familiar minerals transform into new crystal structures that cannot exist anywhere else. The temperature approaches that of the sun's surface. Liquid iron from the outer core may react with the silicate rock of the mantle, creating unusual alloys and compounds. Some scientists think that in this deepest realm, blobs of unusual composition may form and rise as superplumes, massive upwellings that dwarf even the hotspots that create island chains. These superplumes may be responsible for the largest volcanic eruptions in Earth's history, events so massive they can change global climate and trigger mass extinctions. Yet, for all its alien conditions, the deep mantle is intimately connected to the world we know. Every breath you take contains atoms that have journeyed through the mantle's depths. The water in the oceans has been recycled through the planet's interior countless times. The very elements that make up your body were mixed and stirred in the mantle's slow convection, distributed around the globe in the patient circulation of the deep earth. As you rest tonight, suspended on the thin crust above this vast flowing realm, you might imagine yourself as a passenger on a ship sailing across an ocean of stone. Far below, currents of molten rock carry you slowly but surely across the planet's surface, part of a journey that began before life appeared on Earth and will continue long after our sun has dimmed to darkness. The mantle is patient beyond human understanding, yet restless beyond imagination. It never sleeps, never rests, never stops its slow, majestic circulation. It is the engine that has kept our planet geologically alive for more than 4 billion years, ensuring that Earth never becomes the cold, dead world that Mars appears to be today. In this deep sleep beneath, in this dreaming heart of stone and fire, the future of continents is being shaped. New hotspots are forming that will someday birth new islands. Ancient slabs are sinking that will someday alter the chemistry of the deep interior. Convection patterns are shifting that will someday rearrange the face of the earth in ways we cannot yet imagine. So sleep well tonight, cradled by this vast, warm, flowing embrace. You rest upon a planet that dreams in deep time, that breathes with the rhythm of geological ages, that carries you forward on currents of liquid stone. The mantle's sleep is deeper than any dream you will ever have, yet more restless than any waking moment you will ever experience. It is the gentle giant that rocks our world to sleep each night and wakes it up each morning, renewed and ready for another day in the endless dance of stone and fire. The gentle parting of stone patiers, where the earth slowly opens. In the deepest parts of our oceans, in trenches darker than any moonless night, in places where no sunlight has ever dared to venture, something beautiful and patient is happening. If you could somehow visit these abyssal depths, floating like a dreamer through the crushing darkness, you would witness one of the most gentle yet profound processes on our planet, the birth of new ocean floor, the slow, steady parting of the Earth's crust, like the opening of sleeping eyes. Imagine, if you will, the longest mountain range on Earth, stretching not across familiar continents but across the hidden floors of our oceans. This underwater mountain chain winds for more than 60,000 kilometers around the globe like the seam on a baseball, rising from the abyssal plains like a great spine running through the world's waters. This is the mid-ocean ridge system, and it is here that our planet performs its most tender act of creation. The Mid-Atlantic Ridge, perhaps the most famous section of this underwater mountain range, runs like a gentle scar down the center of the Atlantic Ocean from the icy waters near Iceland, all the way south to the frigid seas around Antarctica. Along its length, the seafloor is slowly, almost imperceptibly, pulling apart. It's as if the earth is stretching in its sleep, making room for new dreams, new possibilities, new stone born from the patient fire below. The process happens with such exquisite slowness that it makes the growth of trees seem hurried by comparison. Each year, the two sides of the ridge move apart by just a few centimeters, about the same rate at which your fingernails grow. A person could live their entire life sitting on the ridge crest and never feel the movement, never sense the profound changes happening beneath their feet. Yet this glacial pace, stretched across millions of years, has accomplished something extraordinary. It has opened entire oceans, pushed continents thousands of kilometers apart, reshaped the very face of our planet. The Atlantic Ocean, which today stretches for thousands of kilometers between Europe and America, was born from this process. 200 million years ago, there was no Atlantic at all, just a narrow rift valley where molten rock occasionally bubbled to the surface. To understand how new ocean floor is created, imagine the Earth's crust as a great blanket covering our planet. Along the mid-ocean ridges, this blanket has torn, creating long, narrow gaps where the hot interior of the Earth can peek through. From these gaps, molten rock, magma, rises slowly from the mantle below, like thick honey oozing from a crack in a jar. As this magma reaches the cold ocean water, something magical happens. It cools and hardens instantly, freezing into solid rock in a process that releases great clouds of steam and creates fantastic formations of pillow-shaped lava. These pillow lavas, as geologists call them, stack up like comfortable cushions on the seafloor, each one a snapshot of the moment when fire met water in the darkness of the deep ocean. This newly formed rock pushes against the older seafloor on either side, slowly nudging it away from the ridge like a gentle but persistent hand. The process is so gradual that it's completely invisible to any human observer, yet over geological time, it's powerful enough to move entire continents. Europe and North America are drifting apart at about the same rate that your hair grows, a pace so slow it seems like stillness, yet persistent enough to have opened an entire ocean over the course of Earth's patient history. The chemistry of this underwater creation is as gentle as its pace. The magma that rises at mid-ocean ridges is not the violent, explosive type that creates dramatic volcanic eruptions on land. Instead, it's a quiet, iron-rich rock called basalt that flows like thick cream and hardens into the dark, dense foundation of the ocean floor. This basalt is Earth's most common rock, the steady, reliable building material that forms the floor beneath all of our oceans. As new basalt is created at the ridge crest, it carries with it a subtle signature of the time it was born. The Earth's magnetic field, that invisible shield that protects us from harmful solar radiation, occasionally reverses itself over geological time. North becomes south, south becomes north, in a slow magnetic dance that scientists don't fully understand. When basalt cools and hardens, it locks in the direction of the magnetic field at that moment, creating permanent records of these ancient magnetic reversals. These magnetic stripes, frozen into the ocean floor, create a beautiful symmetrical pattern on either side of spreading ridges. Like tree rings recording years of growth, these magnetic bands record the steady opening of ocean basins, providing scientists with a precise chronometer for measuring the pace of seafloor spreading. It was the discovery of these magnetic patterns in the 1960s that finally convinced skeptical geologists that continents really do drift across the Earth's surface. But the mid-ocean ridges are more than just factories for new ocean floor. They are also oases of life in the deepest, most seemingly barren parts of our planet. Along the ridge crests, where hot water meets cold in the absolute darkness of the deep sea, extraordinary communities of creatures thrive without any energy from the sun. These are the hydrothermal vent fields, underwater gardens where towering chimneys of mineral-rich rock spew superheated water into the frigid abyss. Around these vents, in conditions that would seem impossible for life, entire ecosystems flourish. Giant tube worms, longer than baseball bats, and lacking any mouth or stomach, host bacteria in their tissues that convert the chemical energy in the vent water into food. Ghostly white crabs scuttle through forests of these swaying worms, peculiar fish with antifreeze proteins in their blood, swim through clouds of warm, mineral-rich water. These deep-sea communities represent one of the most remarkable discoveries of the 20th century, life that depends not on photosynthesis, but on chemosynthesis, organisms that have learned to eat the very rocks and chemicals of the Earth itself. They hint at the possibility that life might exist in similar environments elsewhere in our solar system, perhaps in the subsurface oceans of Jupiter's moons, or in the chemical-rich waters beneath the ice of Saturn's Enceladus. The process of seafloor spreading is not uniform across all the world's ridges. Some spread quickly, by geological standards. The East Pacific Rise, which runs up the western coast of the Americas, opens at a rate of several centimeters per year, making it one of the fastest spreading ridges on Earth. Others creep apart more slowly, like the Mid-Atlantic Ridge, which widens at barely 2 centimeters per year. These differences in spreading rate create different landscapes on the seafloor. Fast-spreading ridges tend to be broad, gentle swells with relatively smooth surfaces, while slow-spreading ridges are often deeply rifted, with steep walls and rugged terrain. The slow-spreading ridges also tend to be more volcanically active, with more frequent eruptions of pillow lavas and more dramatic hydrothermal activity. Occasionally, these underwater volcanic eruptions can be truly spectacular events, even though they happen miles beneath the ocean's surface where no human eyes can witness them. In 1993, scientists detected a massive underwater eruption on the Wanda Fuca Ridge off the coast of the Pacific Northwest. The eruption was so large that it changed the temperature and chemistry of the seawater for miles around, killing many of the vent creatures and creating new lava flows that buried existing seafloor. Yet even these dramatic events are part of the gentle, ongoing process of ocean creation. The new lava flows quickly become colonized by new generations of deep-sea creatures. The chemistry of the water returns to normal. The ridge continues its patient work of pulling apart and filling the gap with new rock grain by grain, flow by flow, year by year. On land, we can sometimes see this process of rifting in its early stages. The Great Rift Valley of East Africa is perhaps the best example, a great crack in the continent that stretches for thousands of kilometers from the Red Sea in the north to Mozambique in the south. Here, the African continent is slowly pulling apart, creating a landscape of steep-walled valleys, soda lakes, and active volcanoes. The East African Rift is like a preview of what the Mid-Atlantic Ridge might have looked like in its earlier stages, when the supercontinent Pangaea first began to crack and separate. The rift valleys fill with water from rivers and occasional connections to the sea, creating long, narrow lakes like Tanganyika and Malawi. Volcanic activity along the rift creates fertile soils that support rich ecosystems, making the rift valleys some of the most biodiverse places on Earth. If the rifting continues and geologists believe East Africa will eventually separate from the rest of the continent, creating a new ocean basin between them, Somalia and the Horn of Africa will become an island, drifting slowly eastward as new ocean floor spreads between it and the African mainland. The process will take millions of years, proceeding at the same patient pace that opened the Atlantic and separated the Americas from Europe and Africa. This is the beauty of seafloor spreading. It is creation in the gentlest possible sense. No violent explosions, no sudden catastrophic changes, just the steady, patient work of making new ocean floor, centimeter by centimeter, year by year, eon by eon. It's like watching the earth knit itself a new sweater, one stitch at a time, with needles made of molten rock and threads spun from the deep currents of the mantle. The newly created ocean floor doesn't stay at the ridge forever, like a slow conveyor belt. It moves away from its birthplace, carrying with it a cargo of sediments that rain down from the ocean above, the microscopic shells of tiny sea creatures, particles of dust blown from distant continents, occasional meteorites from space. Over millions of years, these sediments build up into layers that tell the story of Earth's climate, its changing life forms, its periodic mass extinctions and recoveries. This seafloor, born at the ridges and moving slowly outward, eventually reaches the edges of ocean basins where it meets the continental margins, and there, in another act of the Earth's patient recycling, it often disappears back into the mantle through the process of subduction, diving beneath the lighter continental crust, like a gentle whale returning to the depths. But that is another chapter in our story. For now, rest in the knowledge that even in the deepest, darkest parts of our oceans, creation continues. New rock is being born at this very moment, pushing outward with invisible persistence, widening the seas grain by grain. The Earth is literally growing larger as new crust is added to its surface, though the process is so gradual that the planet's overall size remains essentially constant as old crust is recycled elsewhere. As you drift towards sleep tonight, you might imagine yourself floating in those abyssal depths, witnessing the birth of new ocean floor. Picture the gentle upwelling of molten rock, the quiet hiss as it meets the cold water, the steady accumulation of new basalt on the seafloor. It's happening right now beneath miles of dark water, in a rhythm that has continued for billions of years and will continue for billions more. The Earth is always making itself anew, always creating fresh surfaces for life to colonize, always opening new spaces for its restless dreams. In the deepest sleep of the ocean, in the quietest places on our planet, the most profound act of creation continues, the gentle parting of stone that has reshaped our world and will continue reshaping it long after our own small dreams have faded into the patient memory of the deep. The tender collision when continents embrace. There are moments in the Earth's long dreaming when something extraordinarily beautiful happens, when two vast pieces of the planetary puzzle drift toward each other across the slow currents of geological time and meet in the gentlest collision imaginable. Unlike the violent crashes we might picture when we hear the word collision, these meetings of continents are tender embraces that unfold over millions of years, creating some of the most magnificent landscapes our planet has ever known. Picture, if you will, two enormous sleepers slowly approaching each other across a bed the size of an ocean. They move with the patience of glacial ice, the persistence of growing trees, the inevitability of sunrise. Neither is willing to yield, neither can step aside, and so when they finally meet, they have no choice but to embrace, pressing together with a gentleness that can only be achieved by forces so vast and so patient that they measure their progress in the rise and fall of species, in the birth and death of entire ecosystems. The most spectacular example of this continental courtship is still unfolding today in the towering peaks of the Himalayas, where the Indian subcontinent continues its ancient dance with the Asian landmass. About 50 million years ago, a mere blink of an eye in geological time, though an eternity by human standards, India was not the familiar triangular peninsula we know today. Instead, it was an island continent, a massive fragment of ancient Gondwana, drifting northward across the warm waters of the Tethys Sea like a continent-sized ship sailing toward a distant shore. India's journey began much earlier, when the great supercontinent Gondwana began to break apart about 180 million years ago. As the pieces of this ancient landmass slowly separated, India found itself alone on a remarkable voyage, racing northward, if we can call a few centimeters per year racing, across thousands of kilometers of ocean toward its destiny with Asia. The collision, when it finally began, was not a single dramatic event, but rather a prolonged embrace that continues to this day. As India pressed into the southern edge of Asia, the ocean floor between them was gradually consumed, folded, and crumpled like blankets being pushed together from both ends. The seafloor sediments that had accumulated in the Tethys Sea over millions of years were caught between the converging continents, compressed and heated, and transformed into new types of rock. But the most remarkable transformation was yet to come, as the two continental masses continued to push together. neither was dense enough to sink into the mantle below. Continental crust, being lighter than the oceanic crust, simply refuses to subduct under normal circumstances. Instead, the collision began to crumple the very surface of the Earth, folding layers of rock upward like a slow-motion accordion, creating what would eventually become the highest mountain range on our planet. The birth of the Himalayas was not a violent upheaval, but rather the most patient construction project ever undertaken. Layer upon layer of ancient seafloor, lifted far above sea level, began their transformation into the towering peaks we know today. Limestone that had formed on tropical ocean floors millions of years earlier found itself thrust upward into the thin, cold air above the clouds. Fossils of ancient marine creatures, embedded in rock when the world was young, began a journey toward the summit of mountains that would not reach their full height for millions of years to come. Today, near the peak of Mount Everest, climbers can find rocks containing the fossils of sea lilies, delicate, flower-like creatures that lived in warm, shallow seas when India was still far from its Asian destiny. These fossils serve as gentle reminders that even the highest places on Earth were once beneath the waves, part of the slow circulation that continually reshapes our planet's surface. The collision between India and Asia is still active, still ongoing. India continues to push northward at about 4 centimeters per year, roughly the rate at which your fingernails grow. And this persistent pressure keeps the Himalayas rising. Mount Everest gains a few millimeters of height each year, though this growth is partially offset by erosion from wind, water, and ice. The mountain is quite literally still under construction, still growing, still reaching toward the stars with the patience of geological time. But the effects of this continental embrace extend far beyond the obvious majesty of the world's highest peaks. The collision has created a zone of crumpling and folding that extends for thousands of kilometers across Central Asia. The Tibetan Plateau, often called the roof of the world, is perhaps the most dramatic example. A vast high-altitude plain the size of Western Europe, lifted to an average elevation of more than 4 kilometers above sea level by the continuing pressure of India's northward push. This plateau has profoundly influenced the climate of much of Asia and beyond. Its great height forces air masses to rise as they pass over it, cooling them and wringing out their moisture as snow and rain. The resulting precipitation feeds the great rivers of Asia, the Ganges, the Brahmaputra, the Yangtze, the Yellow River, the Indus, the Mekong, which in turn provide water for more than 1 billion people. In a very real sense, the slow collision of two continents continues to shape the daily lives of a significant portion of humanity. The Himalayas are not the only mountains born from continental collision. The Alps, those iconic peaks that rise so dramatically from the plains of Europe, tell a similar story of patient convergence. About 100 million years ago, Africa began its slow drift northward toward Europe, gradually closing the ancient Tethys Sea that once separated them. As the distance narrowed over tens of millions of years, the seafloor sediments between the continents were compressed, heated, and folded into the complex structures we see today. The collision that created the Alps was complicated by the fact that it wasn't simply two large continents meeting head-on, but rather a complex dance involving smaller pieces of crust, microplates, and fragments of ancient ocean floor. Italy, for example, was once a separate piece of Africa that broke away and drifted northward independently, eventually colliding with southern Europe and helping to create the distinctive boot shape of the Italian peninsula. Even today, the collision continues. Africa is still pushing northward into Europe at about 2 centimeters per year, slowly closing the Mediterranean Sea and promising that, in some distant future, the two continents will be joined by new mountain ranges rising from what is now the seafloor between Sicily and North Africa. The Appalachian Mountains of eastern North America tell the story of even more ancient continental collisions. These now gentle, rounded peaks were once as high and sharp as today's Himalayas, raised by the collision between North America and Africa. during the assembly of the supercontinent Pangaea about 300 million years ago. Time and weather have since worn them down, softening their profiles and reducing their heights, but their roots still extend deep into the Earth's crust, testament to the enormous forces that once created them. What makes these continental collisions so fascinating is not just their scale, but their tenderness. Despite the unimaginable forces involved, pressures that can transform solid rock into new minerals, temperatures that can cause mountains to flow like putty, the process unfolds with a gentleness that seems almost impossible to believe. Mountains rise, not in sudden, violent upheavals, but grain by grain, millimeter by millimeter, year by year, with the patience of growing plants reaching toward the sun. The creatures that live on these slowly rising lands often have time to adapt to the changing conditions. As mountains rise and valleys deepen, rivers change their courses, climates shift, and new ecological niches appear. The slow pace of mountain building allows evolution to keep pace, creating new species adapted to high-altitude conditions, cold temperatures, and thin air. In the Himalayas, for example, we find snow leopards perfectly adapted to hunting on steep, rocky slopes, yaks with enlarged lungs and hearts to cope with the thin air, rhododendrons that bloom in brilliant colors against backgrounds of snow and stone. These are not creatures that suddenly appeared when the mountains reached their present height, but species that evolved alongside the rising peaks, adapting generation by generation to the slowly changing conditions. The collision zones where continents meet are also places of remarkable geological diversity. The intense pressure and heat generated by continental collision create new types of rocks through the process of metamorphism. Limestone becomes marble, sandstone becomes quartzite, shale becomes slate, and granite becomes gneiss. These metamorphic rocks often display beautiful patterns of folding, swirling, and banding that tell the story of the forces that created them. Precious stones are often born in these collision zones as well. The heat and pressure can concentrate rare elements into gem-quality crystals, garnets, sapphires, emeralds, and rubies that form deep in the heart of mountain ranges and are only revealed when erosion strips away the overlying rock. Some of the world's most valuable gemstones have made their own slow journey from the depths of continental collision zones to the surface, where they catch the light and remind us of the hidden beauty created by the Earth's patient forces. As you rest tonight, perhaps you can imagine the continents as vast, slow dancers, moving to music played on a timescale we can barely comprehend. India continues its ancient waltz with Asia, Africa maintains its patient advance toward Europe, and somewhere in the deep future, new collisions are being choreographed by the restless motion of the plates beneath our feet. These continental embraces remind us that even the most dramatic features of our planet are born not from violence but from persistence. The highest mountains, the deepest valleys, the most spectacular landscapes all emerge from the same gentle pressure applied over unimaginable spans of time. They are monuments to patience, testaments to the power of slow, steady forces working across the vast expanses of geological time. In the tender collision of continents, we see perhaps the most beautiful expression of the Earth's restless creativity, the ability to take two separate pieces of the planetary puzzle, and through nothing more than gentle, persistent pressure, create landscapes so magnificent. They take our breath away. The mountains that scrape the sky above us are love letters written in stone, the physical expression of the planet's endless capacity for bringing separate things together in the most beautiful possible way. The Earth's gentle recycling mouths, where ocean floors return to dreams. In the grand, slow circulation of our planet's surface, there must be places where the story comes full circle, where the ocean floor that was born with such patient tenderness at the mid-ocean ridges eventually finds its way back to the deep dreams from which it came. These places exist at the edges of ocean basins, in some of the most profound and mysterious locations on Earth, the subduction zones, where oceanic crust politely bows its head and slides back into the warm embrace of the mantle below. If you could visit one of these remarkable places, though you would need to descend through miles of dark ocean water to reach them, you would find yourself at the edge of the deepest trenches on our planet. These are not mere valleys or canyons, but profound gashes in the ocean floor, chasms so deep that if you could somehow drain all the water from them and place Mount Everest at their bottom, the mountain's peak would still be more than 2 kilometers below the ocean's surface. The deepest of these trenches is the Mariana Trench in the western Pacific, a curved scar in the seafloor that plunges nearly 11 kilometers into the Earth's crust. To put this extraordinary depth in perspective, if you could drill straight down through the Mariana Trench, you would travel farther into the Earth than most commercial airplanes fly above it. It is a place where the pressure is more than 1,000 times greater than at sea level, where the water temperature hovers just above freezing, despite being closer to the Earth's molten interior, where darkness is so complete that it seems to have physical weight. Yet even in this most extreme environment on our planet's surface, life finds a way to flourish. Strange, translucent creatures drift through the abyssal depths like living ghosts. Bacteria thrive in conditions that would instantly destroy any surface-dwelling organism. And at the very bottom of the trench, in pressures that would crush a human body in milliseconds, tiny amphipods, shrimp-like creatures no bigger than your thumb, scuttle across the sediment-covered floor, feeding on the organic matter that drifts down from the sunlit world far above. But the trenches are more than just extreme environments for specialized life forms. They are also the entry points where oceanic crust begins its long journey back into the Earth's interior. The process begins when two tectonic plates meet at what geologists call a convergent boundary. If one of the plates carries oceanic crust and the other carries continental crust, the denser oceanic plate will gradually begin to sink beneath its lighter neighbor, like a swimmer diving beneath the surface of a pool. This sinking, called subduction, happens with the same geological patience that characterizes all of the Earth's major processes. The oceanic plate doesn't plunge suddenly into the depths like a stone dropped into water. Instead, it descends at an angle, sliding slowly beneath the continental plate at rates measured in centimeters per year, about as fast as your hair grows, about as quickly as a tree adds new growth rings. As the oceanic plate descends, it carries with it not just the basalt that formed at mid-ocean ridges, but also the accumulated sediments of millions of years, the tiny shells of countless microscopic sea creatures, particles of dust that blew from distant continents, volcanic ash from eruptions on far-off islands, even occasional meteorites that fell from space and settled on the ocean floor. All of this material, compressed into layers like the pages of an enormous book, begins its slow journey back into the Earth's interior. The descent is not always smooth. As the subducting plate slides beneath its neighbor, friction between the two massive pieces of crust can cause them to stick and slip, storing up tension for decades or centuries before releasing it in earthquakes. The most powerful earthquakes on Earth, the magnitude 9.0 earthquake that struck Japan in 2011, the devastating 2004 Indian Ocean earthquake that triggered the deadly tsunami, occur at subduction zones where this stick-slip process releases the accumulated stress of years or centuries in a matter of minutes. But even these dramatic events are just brief interruptions in the plate's patient journey into the depths. As it descends, the subducting oceanic crust encounters increasing temperature and pressure. Water that had been chemically bound in the crystal structure of minerals begins to be released, rising upward into the overlying mantle and lowering its melting point. This process creates magma molten rock that is less dense than the surrounding solid rock, and therefore begins to rise toward the surface. This rising magma doesn't always reach the surface immediately. Often it collects in underground chambers where it slowly cools and crystallizes, forming the great granite masses that make up the cores of mountain ranges. But sometimes the magma does reach the surface, creating the chains of volcanoes that are found along most subduction zones. These volcanic arcs are some of the most spectacular features on Earth. The Andes Mountains of South America, stretching like a spine down the western coast of the continent, were built by subduction of the oceanic Nazca Plate beneath the South American continent. The explosive volcanoes of Japan, Indonesia, and the Philippines are all products of oceanic plates sliding beneath the edges of Asia. The volcanic peaks of the Cascade Range in the Pacific Northwest, Mount Rainier, Mount Baker, Mount St. Helens, owe their existence to the subduction of the small Juan de Fuca Plate beneath North America. These volcanoes are not random or chaotic in their distribution. They form remarkably regular chains, typically located about 100 to 200 kilometers inland from the oceanic trench where subduction begins. This consistent spacing reflects the depth at which the subducting plate releases enough water to trigger melting in the overlying mantle, a depth that is largely controlled by the temperature and pressure conditions within the Earth. The ring of fire that surrounds much of the Pacific Ocean is perhaps the most famous example of this subduction-related volcanism. From the explosive peaks of Alaska and the Aleutian Islands, down through the Cascades of the Pacific Northwest, the volcanic mountains of Central and South America, across to New Zealand, up through Indonesia and the Philippines, and north through Japan and the Kamchatka Peninsula of Russia. This ring of active volcanoes marks the locations where oceanic plates are actively subducting beneath their continental neighbors. But subduction is not just about the creation of volcanoes and the occurrence of earthquakes. It is also the Earth's primary recycling mechanism, the process by which old oceanic crust is returned to the mantle and eventually remelted and reformed into new rock. Without subduction, the Earth's surface would gradually be covered by ever-thickening layers of oceanic crust, and the dynamic process of plate tectonics would eventually grind to a halt. As the subducting plate descends deeper into the Earth, it encounters temperatures hot enough to begin breaking down the minerals that formed at the cool, high-pressure conditions of the deep ocean floor. The water that was incorporated into the crystal structure of these minerals is gradually released, rising upward and helping to keep the overlying mantle hot and mobile. Some scientists believe that this water circulation between the Earth's surface and interior may be crucial for maintaining the planet's long-term habitability. The deepest parts of subducting plates may descend all the way to the core mantle boundary, nearly 3,000 kilometers below the surface. There they may contribute to the formation of large, hot blobs of unusual composition that eventually rise back toward the surface as the mantle plumes that create hotspot volcanoes like those of Hawaii and Iceland. In this way, rock that formed on the ocean floor may eventually return to the surface in a completely different location after a journey that lasted hundreds of millions of years. The process of subduction also plays a crucial role in concentrating valuable minerals. As oceanic crust is heated and compressed during its descent, metals like copper, gold, silver, and platinum can be concentrated into ore deposits that are later exposed when mountain ranges are uplifted and eroded. Many of the world's richest mining districts are located in ancient subduction zones, where these concentration processes operated millions of years ago. Perhaps most remarkably, subduction may also play a role in the long-term regulation of Earth's climate. Carbon dioxide dissolved in seawater can be incorporated into the minerals that form on the ocean floor. When these minerals are subducted, some of this carbon is carried into the Earth's interior, while some is released through volcanic activity. This carbon cycle, operating over millions of years, may help to regulate the amount of carbon dioxide in the atmosphere and thus the planet's temperature. The subduction zones where oceanic crust returns to the mantle are places of profound geological activity, but they are also places of extraordinary beauty. The deep trenches themselves, though hidden beneath miles of dark water, have a stark alien beauty that rivals any landscape on the surface. The volcanic arcs that rise above subduction zones create some of the most spectacular mountain scenery on Earth. from the snow-capped peaks of the Andes to the graceful volcanic cones of Japan. These are also places where the Earth's interior and exterior are most intimately connected. Water from the oceans descends with the subducting plates, carrying dissolved chemicals and gases into the deep Earth. Gases and heat from the mantle rise through the volcanic arcs, bringing messages from the planet's interior to the surface. In subduction zones, the solid Earth and the hydrosphere, the atmosphere and the biosphere, are all linked together in complex cycles of exchange and transformation. As you rest tonight, you might imagine the great slow circulation that carries the ocean floor from its birth at mid-ocean ridges to its return to the mantle at subduction zones. It is a journey measured not in miles or kilometers, but in tens of millions of years. It is a circulation so vast and so patient that entire evolutionary epochs can pass during a single cycle, yet so persistent that it has been reshaping the Earth's surface for billions of years. In the gentle recycling of oceanic crust, we see perhaps the most profound expression of the Earth's commitment to renewal and change. Nothing on our planet's surface is permanent, nothing is forever. Even the most solid-seeming rock is part of a vast circulation that connects the deepest interior to the highest peaks, the hottest magma to the coldest deep-sea trenches, the newest volcanic islands to the most ancient continental cores. This is the Earth's way of staying young, of keeping itself geologically alive and active. Through the patient process of subduction, our planet continually renews itself, ensuring that its surface remains a dynamic, ever-changing stage for the endless drama of life, weather, and geological transformation. In the deepest places on Earth, old ocean floors return to dreams, only to be reborn in new forms, in new places, in the endless dance of stone and fire that keeps our world forever young. The slow breathing of volcanoes, Earth's gentle exhalations. In certain blessed places around our world, the Earth breathes fire, though even this most dramatic expression of our planet's inner life unfolds with a patience and gentleness that might surprise you. Volcanoes are not the violent, explosive monsters that popular imagination often makes them out to be. They are, instead, like great sleeping giants who occasionally sigh in their dreams, releasing the accumulated warmth of the planet's heart in long, slow exhalations that can last for days, weeks, or even years. Picture, if you will, the Earth as an enormous dreamer, occasionally stirring in its sleep, shifting position, sighing deeply as it settles into a more comfortable arrangement. The volcanoes scattered across our planet's surface are like the gentle breathing of this vast sleeper, the soft exhalations that release the heat and pressure that build up in the planet's deep interior over thousands and millions of years. Most volcanic eruptions are not the catastrophic explosions that make headlines and fill movie screens with spectacular destruction. They are instead quiet affairs, as gentle as the breath that rises from your lips on a cold morning. The volcanic islands of Hawaii, for example, grow not through violent explosions but through the patient accumulation of countless small lava flows, each one adding a few centimeters to the island's height, a few meters to its shoreline, like a master craftsman slowly, methodically building a sculpture that will take millennia to complete. Kilauea, the most active volcano on the big island of Hawaii, has been erupting almost continuously for decades. Yet its eruptions are so gentle that tourists can often walk within a few hundred meters of active lava flows. The lava that emerges from the volcano is hot, more than 1,000 degrees Celsius, but it flows with the consistency of thick honey, moving so slowly that a person walking at normal pace can easily outrun it. This is the Earth's breathing at its most peaceful, the slow exhalation of molten rock that builds new land grain by grain, flow by flow. These Hawaiian volcanoes are fed by what geologists call a hotspot, a column of unusually hot rock that rises from deep in the Earth's mantle, perhaps from as far down as the core mantle boundary, nearly 3,000 kilometers below the surface. Like a blowtorch held beneath a sheet of metal, this hotspot melts through the oceanic crust above it. creating volcanoes that build upward from the ocean floor. But the Pacific Plate, carrying the Hawaiian chain, doesn't stay still above this hotspot. It moves northwestward at about 4 centimeters per year, roughly the same rate at which your fingernails grow, carrying each volcano away from its source of magma-like islands, drifting away from their birthplace. As each volcano moves away from the hotspot, it becomes dormant, its supply of fresh magma cut off. Meanwhile, new volcanoes form over the hotspot, creating the chain of islands we see today. This process has been going on for millions of years, creating not just the current Hawaiian Islands, but also a long chain of submerged mountains stretching across the Pacific Ocean floor. The Emperor Sea Mounts, underwater peaks that extend northward from the Hawaiian chain, are the ancient remnants of volcanoes that formed over the same hotspot tens of millions of years ago, before the Pacific Plate changed direction and began carrying them northwestward instead of due north. Iceland sits atop another such hotspot, one that happens to coincide with the mid-Atlantic ridge where Europe and America are slowly pulling apart. Here, the combination of seafloor spreading and hotspot volcanism creates one of the most geologically active places on Earth. Yet even here, the volcanic activity is usually gentle and predictable. Most Icelandic eruptions are what volcanologists call effusive. They pour out steady streams of lava rather than exploding violently. The 2010 eruption of Eyjafjallajökull, which disrupted air travel across Europe for weeks, was unusual not because it was particularly violent, but because it occurred beneath a glacier. When hot lava met ice, it created enormous clouds of steam and ash that rose high into the atmosphere. But the eruption itself was relatively gentle by volcanic standards, more like a giant steam engine releasing pressure than a violent explosion. Some of the most beautiful volcanic eruptions occur along the mid-ocean ridges, hidden beneath miles of dark seawater, where no human eyes can witness them directly. When magma erupts into the cold ocean water, it cools instantly, forming the distinctive pillow-shaped lava flows that make up much of the ocean floor. These underwater eruptions are usually completely silent from a human perspective, marked only by slight changes in water temperature and chemistry that sensitive instruments can detect. The ring of fire that encircles much of the Pacific Ocean is studded with volcanic peaks, from the snow-capped stratovolcanoes of the Andes to the elegant cones of Japan's Mount Fuji. These volcanoes, formed by the subduction of oceanic plates beneath continental margins, can be more explosive than their hotspot cousins, but they too spend most of their time in peaceful slumber, stirring only occasionally to release the pressure that builds up as oceanic crust melts in the depths below. Mount Rainier in Washington state, for example, is considered one of the most potentially dangerous volcanoes in the United States because of its proximity to major population centers, yet it has been dormant for more than a century. Like most volcanoes, it spends the vast majority of its time sleeping peacefully, its slopes covered with glaciers and alpine meadows, its summit often wreathed in lenticular clouds that form as air currents flow over its gentle dome. When these subduction zone volcanoes do erupt, they often do so with a violence that reflects the different chemistry of their magma. Unlike the iron-rich basalt that flows so peacefully in Hawaii, the magma that forms from melted oceanic crust is often richer in silica, making it thicker, stickier, and more prone to explosive eruptions. But even these explosive eruptions are usually preceded by weeks or months of warning signs: increased seismic activity, changes in the temperature of volcanic gases, subtle swelling of the volcano's slopes as magma rises from below. The 1980 eruption of Mount St. Helens, one of the most famous volcanic eruptions in recent US history, was preceded by 2 months of increasingly intense earthquake activity. The eruption itself, while spectacular and destructive, lasted only about 9 hours. In the decades since, the volcano has returned to its peaceful slumber, its slopes slowly being recolonized by plants and animals, its crater gradually filling with a new lava dome that grows imperceptibly year by year. This pattern of long sleep punctuated by brief activity is typical of most volcanoes around the world. They spend decades, centuries, or even millennia in quiet repose, their internal fires banked low, their magma chambers slowly cooling and crystallizing. During these peaceful interludes, they become part of the landscape, their slopes providing rich soil for agriculture, their peaks serving as landmarks and sources of fresh water from melting snow and ice. The volcanic soils that form from weathered lava are among the most fertile on Earth. The slopes of Mount Vesuvius in Italy, despite the volcano's fearsome reputation, support some of the richest farmland in Europe. The coffee that grows on the volcanic slopes of Central America and Indonesia owes much of its distinctive flavor to the mineral-rich soils created by ancient eruptions. In a very real sense, volcanoes are gardeners, patiently preparing the soil for future harvests with their slow exhalations of mineral-rich rock. Even the most explosive volcanic eruptions, viewed from the perspective of geological time, are brief interruptions in long periods of peaceful quiet. The eruption of Krakatoa in 1883, which was heard 3,000 kilometers away and created spectacular sunsets around the world for months afterward, lasted only about 22 hours. The massive eruption of Mount Tambora in 1815, which caused global climate effects and created the year without a summer, was essentially over within a few days. These dramatic events, while significant for human observers, are like brief sneezes in the long, slow breathing of the Earth. Most volcanic eruptions produce far more beauty than destruction. The aurora-like glow of lava fountains against the night sky, the graceful curtains of volcanic gas and steam rising into the atmosphere, the otherworldly landscapes of fresh lava flows cooling under starlight. These are among the most spectacular natural phenomena our planet has to offer. Even the ash clouds that sometimes accompany eruptions can create breathtaking sunsets as fine particles scatter sunlight in unusual ways. The volcanic islands scattered across the world's oceans are perhaps the most beautiful expressions of the Earth's volcanic breathing. The Galapagos Islands, the Azores, the Canary Islands, the islands of French Polynesia, all of these are gifts from the planet's interior, places where the deep Earth has exhaled enough molten rock to build new land in the middle of the sea. Each island is a unique ecosystem, a laboratory of evolution where life has adapted to volcanic landscapes in remarkable ways. On the volcanic island of Surtsey, which emerged from the sea near Iceland in 1963, scientists have been able to observe in real time how life colonizes new volcanic land. Within just a few decades, the barren lava flows have been colonized by mosses, grasses, and eventually shrubs and trees. Birds nest on the cliffs formed by cooling lava, while marine life flourishes in the tide pools carved by wave action into the volcanic rock. The deep-sea volcanic vents along mid-ocean ridges host some of the most extraordinary ecosystems on Earth. In the complete darkness of the abyssal depths, where crushing pressure and near-freezing temperatures would seem to make life impossible, communities of strange creatures thrive around the warm water that emerges from volcanic chimneys. Giant tube worms without mouths or stomachs, ghostly white crabs, and bizarre fish with antifreeze proteins in their blood all depend on the chemical energy released by the Earth's volcanic exhalations. These deep-sea volcanic ecosystems may provide clues to how life first evolved on Earth billions of years ago, when the planet's surface was very different from what we know today. They also suggest that life might exist in similar environments elsewhere in the solar system, perhaps around volcanic vents in the subsurface oceans of Jupiter's moon Europa or Saturn's moon Enceladus. Volcanoes also play a crucial role in the Earth's long-term climate system. The carbon dioxide released by volcanic eruptions adds to the greenhouse effect, helping to warm the planet, while the sulfur compounds released by some eruptions can have a cooling effect by reflecting sunlight back to space. Over geological timescales, These volcanic emissions help regulate the Earth's temperature, preventing it from freezing solid like Mars or becoming a hellish greenhouse like Venus. The largest volcanic eruptions in Earth's history, the massive flood basalt eruptions that covered vast areas with thick layers of lava, may have triggered major climate changes and mass extinction events. The Siberian traps, formed by enormous volcanic eruptions about 252 million years ago, may have contributed to the Permian-Triassic extinction event, the most severe mass extinction in Earth's history. Yet even these massive eruptions, while devastating in their immediate effects, ultimately helped create new ecological niches and may have paved the way for new forms of life to evolve. The Yellowstone supervolcano, one of the most famous volcanic systems in North America, illustrates the difference between popular perception and geological reality. While sensationalized accounts often portray it as an imminent threat to civilization, geologists know that it has been dormant for about 70,000 years and shows no signs of an imminent eruption. Like most volcanoes, it spends the vast majority of its time sleeping peacefully, its underground magma chamber slowly cooling and crystallizing. During its long periods of dormancy, the Yellowstone region has become one of America's most beloved national parks, famous not for volcanic destruction but for its geysers, hot springs, and diverse wildlife. The geothermal features that attract millions of visitors each year are gentle expressions of the volcanic heat below, the Earth's way of releasing pressure gradually rather than catastrophically. Old Faithful, Yellowstone's most famous geyser, erupts with remarkable regularity about every 90 minutes, sending a column of hot water and steam about 50 meters into the air. This predictable performance is like a volcanic heartbeat, a regular pulse that reminds us of the fire that lies beneath the peaceful landscape. The geyser's eruptions are so gentle that visitors can sit just a few dozen meters away and watch in perfect safety. The volcanic landscapes of the world tell stories that span millions of years, stories written in layers of lava and ash, in the graceful curves of cinder cones and the dramatic profiles of stratovolcanoes. The Giant's Causeway in Northern Ireland, with its spectacular hexagonal basalt columns, was formed when a massive lava flow cooled and contracted about 50 million years ago. Devil's Tower in Wyoming is the eroded remnant of an ancient volcanic neck, the hard core of a volcano whose softer outer layers have been worn away by millions of years of wind and rain. These ancient volcanic landscapes remind us that the Earth's breathing has been going on for billions of years, creating and destroying, building up and wearing down, in an endless cycle of renewal. The volcanoes that are active today are just the latest chapter in a story that began when the Earth was young and will continue long after our own species has become part of the geological record. As you settle into sleep tonight, you might imagine the gentle breathing of the Earth's volcanoes around the world. In Hawaii, lava flows quietly down the slopes of Kilauea, adding new rock to the island's growing bulk. In Iceland, geysers send columns of heated groundwater into the Arctic air. Along the mid-ocean ridges, pillow lavas form in the crushing darkness of the deep sea, creating new ocean floor grain by grain. In the Ring of Fire, sleeping giants rest peacefully, their internal fires banked low, dreaming of future eruptions that may not come for decades or centuries. This is the Earth's way of staying warm, of releasing the heat that has been building in its interior since the planet's formation 4.5 billion years ago. Without this volcanic breathing, the Earth would gradually cool and become geologically inactive, like the Moon or Mars. The volcanoes that occasionally remind us of the fire beneath our feet are also the guardians of our planet's continued geological vitality, ensuring that the Earth remains a dynamic, living world. In the gentle exhalations of volcanoes, we see both the power and the patience of geological processes. They remind us that beneath the familiar landscape of forests and fields, cities and towns, lies a world of unimaginable heat and pressure, a realm of molten rock and slow convection that operates on timescales far longer than human experience. Yet this hidden world makes itself known through the most beautiful expressions, the graceful cones of volcanic peaks, the otherworldly landscapes of fresh lava flows, the warm springs that bubble up from the depths, bringing messages from the Earth's dreaming heart to the surface where we can marvel at their gentle mystery. The secret gardens of the abyss life in the deep ocean's dreams, in the deepest, darkest corners of our oceans, in places where no ray of sunlight has ever penetrated, where the pressure would crush any surface dweller in an instant, where the water is so cold it seems to hover at the very edge of freezing, something wonderful and unexpected flourishes. These are the secret gardens of the abyss, oases of life that thrive not on the energy of the sun, but on the gentle warmth and chemical richness that seeps upward from the Earth's interior. Imagine, if you will, descending through the ocean's layers like a slow-motion falling dream, first through the sunlit surface waters where familiar sea life swims and plays, then through the twilight zone where the last traces of solar energy fade away, finally into the midnight zone where eternal darkness reigns. Down, down, down you drift, past the deepest depths that whales can reach, past the limit where even the hardiest deep-sea fish can survive, until at last you arrive at the ocean floor itself, a vast, seemingly barren plain of fine sediment stretching endlessly in all directions. But if you knew where to look, if you could navigate to one of the special places where the Earth's internal heat finds its way to the surface, you would discover something that seems almost magical. Towering chimneys of mineral-rich rock, some as tall as three-story buildings, releasing plumes of superheated water into the frigid abyss. These are the hydrothermal vents, the ocean's equivalent of hot springs, and around them flourishes some of the most remarkable life our planet has ever created. The water that emerges from these deep-sea chimneys is heated by the same geological processes that drive plate tectonics and volcanic activity. As seawater percolates down through cracks in the oceanic crust, it is heated by contact with hot rock and magma below. This heating process dissolves minerals from the surrounding rock, sulfur compounds, metals like iron and copper, rare elements that are scarce in normal seawater. When this mineral-rich water emerges from the vents, it creates an underwater oasis of chemical energy. The creatures that live around these vents have evolved to harvest this chemical energy directly, without any dependence on sunlight or photosynthesis. Giant tube worms, some as long as baseball bats, anchor themselves near the vents and host colonies of bacteria in their tissues. These bacteria perform a kind of chemistry that seems almost like alchemy, converting the sulfur compounds in the vent water directly into food energy through a process called chemosynthesis. The tube worms themselves are among the most alien-looking creatures on Earth, yet also strangely beautiful. They have no mouth, no stomach, no digestive system at all in the conventional sense. Instead, they depend entirely on their bacterial partners, providing them with a safe home and a steady supply of chemicals in exchange for nutrients. It's a partnership so intimate that neither organism can survive without the other, a collaboration that has been perfected over millions of years of evolution in the deep. Around the tube worms, an entire ecosystem flourishes in the eternal darkness. Ghostly white crabs, their shells translucent in the absence of any need for pigmentation, scuttle through forests of swaying worms. Strange fish with enlarged eyes and antifreeze proteins in their blood cruise through the warm plumes of water. Sea spiders with legs as delicate as spun glass pick their way across mats of bacteria that carpet the vent fields in colors ranging from brilliant white to deep orange to sulfur yellow. These bacterial mats are gardens in the truest sense, though they harvest not sunlight, but chemistry. They spread across the warm rocks around the vents like slow-growing carpets, creating the base of a food web that supports an entire community of creatures. Some bacteria form delicate, lace-like structures that flutter in the gentle currents. Others build sturdy, dome-shaped colonies that can withstand the harsh conditions near the vents. The vent chimneys themselves are marvels of natural architecture, built grain by grain as minerals precipitate out of the hot water and solidify in the cold seawater. They grow like underwater skyscrapers, adding new floors as they build upward toward the distant surface. Some are elegant, slender spires that rise gracefully from the seafloor. Others are massive, bulbous structures that sprawl across the landscape like alien cities. The chimneys are often given colorful names that reflect their appearance: black smokers that emit dark plumes of iron-rich minerals, white smokers that release lighter-colored minerals, beehives that are covered with delicate mineral formations resembling honeycombs. Each type of chimney creates its own microenvironment, its own specialized community of organisms adapted to the particular temperature, chemistry, and flow patterns of that specific vent. Some vents are violent and chaotic, spewing water at temperatures exceeding 400 degrees Celsius, hot enough to melt lead. These superheated vents create their own weather systems, with turbulent plumes of hot water rising like underwater tornadoes. Other vents are gentle and diffuse, releasing warm water through fields of cracks and fissures in a process so gradual it's like watching the seafloor breathe. The life cycles of these vent ecosystems are tied to the geological processes that create and destroy the vents themselves. When tectonic activity or changes in magma flow cut off the supply of hot water to a vent field, the entire ecosystem faces extinction. The tube worms die, the crabs disperse, the bacterial mats fade away, leaving behind only the ghostly mineral chimneys as tombstones marking where life once flourished. But elsewhere along the mid-ocean ridges, new vents are constantly being born, creating new opportunities for life to colonize and establish fresh communities. The larvae of vent organisms are carried by deep ocean currents from dying vent fields to newly formed ones, seeding new gardens in the abyss. It's a cycle of birth, growth, death, and renewal that plays out over years and decades rather than the millions of years typical of geological processes. The discovery of these deep-sea vent communities in the 1970s revolutionized our understanding of life on Earth. Before their discovery, scientists believed that all life ultimately depended on energy from the sun, captured by photosynthesis and passed up through food webs. The vent communities proved that life could exist independently of solar energy, powered instead by the chemical energy released by geological processes. This discovery has profound implications for our search for life elsewhere in the universe. If life can thrive in the extreme conditions around deep-sea vents powered by chemical energy rather than sunlight, then similar communities might exist in the subsurface oceans of Jupiter's moon Europa, Saturn's moon Enceladus, or other worlds where liquid water exists beneath ice-covered surfaces. The vent communities show us that life is more flexible, more creative, more persistent than we ever imagined. The creatures that live around deep-sea vents have evolved remarkable adaptations to their extreme environment. Some have proteins that remain stable at temperatures that would denature the proteins in surface-dwelling organisms. Others have specialized organs for detecting the chemical gradients around vents, allowing them to navigate to the perfect spot where temperature and chemistry provide optimal conditions for survival. Many vent organisms live life in the fast lane, growing quickly and reproducing rapidly to take advantage of the ephemeral nature of their habitat. Some tube worms can grow more than a meter per year, faster than bamboo, one of the fastest growing plants on land. This rapid growth allows them to quickly colonize new vents and build up large populations before the inevitable changes in geological conditions force them to disperse to new locations. The isolation of different vent fields, separated by hundreds or thousands of kilometers of abyssal seafloor, has led to remarkable evolutionary diversity. Each vent field tends to develop its own endemic species, creatures found nowhere else on Earth. Scientists estimate that 90% of the species found at deep-sea vents are completely unknown to science, representing a vast reservoir of biodiversity hidden in the deepest parts of our oceans. These vent communities also play important roles in the global cycling of chemicals between the Earth's interior and its surface. The hot water emerging from vents carries dissolved metals and other elements from deep within the oceanic crust, depositing them on the seafloor, where they can eventually be incorporated into sediments or recycled through the process of seafloor spreading. The biological activity around vents affects the chemistry of these processes, with organisms concentrating certain elements while dispersing others. Some deep-sea vents create deposits of valuable minerals, copper, silver, gold, and rare earth elements that are increasingly important for modern technology. These deposits, built up over thousands of years of vent activity, represent a potential new frontier for mineral extraction, though the extreme depths and delicate ecosystems present enormous technical and environmental challenges. The study of deep-sea vent communities continues to yield new discoveries about the limits of life on Earth. Researchers have found organisms living in temperatures exceeding the boiling point of water, in chemical conditions so extreme they would dissolve human tissue, in pressures that would collapse any air-filled space in seconds. Each new discovery expands our understanding of the conditions under which life can exist and thrive. As you rest tonight in the comfort of your warm bed, you might spare a thought for these secret gardens of the abyss, these alien ecosystems that flourish in the Earth's deepest dreams, kilometers beneath the surface of the sea, in darkness more complete than any earthly night. Communities of strange and beautiful creatures go about their lives, powered by the gentle warmth that seeps upward from our planet's molten heart. These deep-sea oases remind us that life is endlessly creative, finding ways to flourish even in the most unlikely places. They show us that our planet is alive, not just on its sun-warmed surface, but throughout its depths, wherever energy and chemistry create the possibility for living things to take hold and grow. In the secret gardens of the abyss, the Earth's geological dreams give birth to biological realities more wonderful than anything our imagination could devise. The long dance of continents, Pangaea's patient waltz. There was a time, long ago in the deep dreams of geological memory, when all the lands we know today were gathered together in a single vast embrace. Picture it, one enormous continent stretching from pole to pole and halfway around the world, wrapped by a single endless ocean that covered the rest of our planet's surface. This ancient supercontinent, which geologists call Pangaea, meaning all Earth, was like a great island floating in the middle of an endless sea, a gathering place where all the world's lands came together in the most patient dance our planet has ever known. If you could somehow visit Pangaea as it existed about 250 million years ago, you would find yourself in a world almost unrecognizably different from the one we know today. The familiar outlines of continents that we memorize from maps and globes would be impossible to discern, folded together like pieces of an enormous puzzle pressed into a single complex shape, where the eastern coast of North America nestles today against the western shores of Europe and Africa, where India pressed close against Antarctica, and Australia lay comfortably beside the other southern continents that we now know as South America and Africa. At the heart of this vast landmass, far from any ocean, lay enormous deserts that stretched for thousands of kilometers without interruption. These were places where rain rarely fell, where the moisture from the distant sea could not reach, where sand dunes larger than modern countries shifted slowly with winds that blew across landscapes empty of familiar life. It was a harsh interior, yet even in its severity, there was a kind of stark beauty. Red sand beneath alien skies, endless horizons broken only by the occasional mountain range, where pieces of the supercontinent had collided and crumpled together. But Pangaea was not destined to remain whole forever. Like all arrangements of the Earth's restless crust, It carried within itself the seeds of its own transformation. Deep beneath the supercontinent, currents in the mantle were slowly shifting, creating new patterns of heat flow that would eventually tear Pangaea apart and scatter its pieces across the globe in a dance that continues to this day. The breakup began slowly, as all geological processes do, with the formation of great rift valleys across the supercontinent's surface. These were like the first small cracks that appear in a sidewalk before it eventually breaks apart completely. Narrow valleys where the crust was beginning to stretch and thin, where small earthquakes occasionally shook the ground, where volcanic activity hinted at the forces stirring below. One of the first major rifts opened where the Atlantic Ocean would eventually form, separating what would become North America from Europe and Africa. For millions of years, this rift remained a narrow valley, sometimes filled with shallow lakes, sometimes dry, as the continents pulled apart at a rate measured in centimeters per year. Gradually, inexorably, the rift widened, and eventually the ocean began to seep in from the edges, creating the first tentative beginnings of the Atlantic. Another rift opened in what is now the Western Indian Ocean, beginning the separation of Madagascar from the eastern coast of Africa. Still another began to divide the southern continents, preparing for the eventual separation of South America from Africa, Australia from Antarctica, India from its southern neighbors. Like a piece of cloth slowly tearing along multiple seams, Pangaea began to come apart in a process that would take more than 100 million years to complete. The actual breakup, when it began in earnest about 200 million years ago, was not a violent explosion but rather the gentlest possible parting of ways. The fragments of Pangaea drifted apart like lily pads floating on a pond, each moving at its own pace, following its own path across the slowly circulating currents of the mantle below. Some moved quickly by geological standards. India, for example, raced northward across the ancient Tethys Sea at rates approaching 20 centimeters per year, covering thousands of kilometers in just a few tens of millions of years. Others moved more sedately, like the gradual opening of the Atlantic at just a few centimeters per year. As the continents separated, new oceans were born in the spaces between them. The Atlantic grew steadily wider as North and South America drifted westward, while Europe and Africa moved eastward. The Indian Ocean opened as India began its epic journey toward Asia, leaving behind a widening expanse of water, dotted with volcanic islands created by hotspots in the seafloor below. What had once been the single, vast ocean surrounding Pangaea gradually divided into the familiar pattern of Pacific, Atlantic, and Indian Oceans that we know today. The separation of the continents created opportunities for life to evolve in isolation on different land masses. When Pangaea was whole, similar species could spread across the entire supercontinent, leading to relatively uniform flora and fauna worldwide. But as the continents drifted apart, populations became separated by ever-widening oceans, and evolution began to follow different paths on different land masses. This is why we find such striking similarities between the fossils and rock formations on opposite sides of the Atlantic Ocean, yet also such dramatic differences between the modern plants and animals of different continents. The similarities reflect the time when these lands were joined together in Pangaea, while the differences show the results of millions of years of separate evolution after the continents drifted apart. Australia's unique marsupial fauna, for example, reflects the continent's early separation from other landmasses and its long journey across the southern oceans in isolation. When Australia finally broke away from Antarctica about 45 million years ago, it carried with it a cargo of primitive mammals that evolved in isolation into the kangaroos, koalas, and other distinctive species we associate with the continent today. Similarly, South America developed its own unique assemblage of plants and animals during the long period when it was separated from North America by a sea barrier. Giant ground sloths, saber-toothed marsupials, and other exotic creatures evolved in this southern isolation, until the two Americas were finally reconnected by the formation of the Central American land bridge just a few million years ago. The drifting of continents also profoundly affected global climate patterns. When the land masses were grouped together in Pangaea, ocean currents could flow freely around the supercontinent, creating relatively stable, if harsh, climate conditions. But as the continents separated and moved to different latitudes, they began to disrupt these circulation patterns in complex ways. The northward movement of India and its eventual collision with Asia, for example, not only created the Himalayas, but also disrupted the atmospheric circulation patterns that bring monsoon rains to much of southern Asia. The gradual closing of the connection between the Atlantic and Pacific through Central America changed the pattern of ocean currents and may have contributed to the ice ages that have characterized the past few million years of Earth's history. Even today, the dance that began with the breakup of Pangaea continues. The Atlantic Ocean grows wider by a few centimeters each year as the mid-ocean ridge continues to spread. Africa drifts slowly northward toward Europe, gradually closing the Mediterranean Sea and promising new mountain ranges in the distant future. Australia moves northward toward Asia at about 6 centimeters per year, fast enough that its position on maps will need to be updated within our lifetimes. But the most dramatic chapter in the continuing dance may be taking place in East Africa, where the continent is beginning to pull apart along the Great Rift Valley. Here, in a process that eerily mirrors the early stages of Pangaea's breakup, the African plate is slowly splitting into two pieces. The eastern portion, carrying Somalia and the Horn of Africa, is beginning to separate from the main body of the continent. If this process continues, and geologists believe it will, a new ocean will eventually open in East Africa, separating the eastern and western portions of the continent, just as the Atlantic separated the Americas from Europe and Africa hundreds of millions of years ago. The Rift Valley lakes, Tanganyika, Malawi, Turkana, may be early glimpses of this future sea, narrow bodies of water, filling the spaces where the continent is beginning to stretch and thin. Looking even further into the future, some geologists have attempted to predict where the continents will be hundreds of millions of years from now. Computer models suggest that the continents may eventually come together again, forming new supercontinents in configurations we can barely imagine. One scenario, called Pangaea Ultima, envisions the Americas colliding with Africa and Europe as the Atlantic Ocean eventually closes, while another scenario, called Amatia, pictures the continents gathering around the North Pole as the Arctic Ocean closes. These future supercontinents, if they form, will be as temporary as Pangaea was. The Earth's restless energy will eventually break them apart again, sending their fragments on new journeys across the planet's surface in a dance that may continue for billions of years into the future, until our sun grows old and the planet's internal heat finally begins to fade. The story of Pangaea and its patient breakup reminds us that even the largest, most seemingly permanent features of our planet are temporary arrangements in the endless dance of stone and fire. The continents we think of as fixed have wandered thousands of kilometers from their ancient positions. The oceans we consider eternal have opened and closed repeatedly throughout Earth's history. Even the climate patterns and biological communities that seem so stable to us are constantly shifting as the continents continue their slow migration across the planet's surface. Yet there is something deeply comforting about the patience of this continental dance. Changes that might seem catastrophic if they happened quickly unfold, so gradually that life has time to adapt, to evolve, to find new ways of thriving as conditions slowly change. The breakup of Pangaea took more than 100 million years, time enough for entire evolutionary lineages to rise and fall, for new ecosystems to develop and spread, for life to experiment with countless new forms and strategies. As you settle into sleep tonight, you might imagine yourself as a passenger on one of these drifting continents, riding across the Earth's surface on a journey that began before the first dinosaurs walked the land and will continue long after our own species has become part of the fossil record. You are traveling on the grandest voyage ever undertaken, moving at the speed of growing fingernails, but covering distances that span oceans, riding the slow currents of the mantle on a journey that connects the deepest past with the most distant future. In the long dance of continents, we see perhaps the most beautiful expression of the Earth's creative patience. Nothing is forever, nothing is fixed, but everything is connected in the great circulation that carries land and sea, mountain and valley, through endless cycles of coming together and drifting apart. It is a dance without beginning or end, a waltz played on the grandest possible stage, with partners as vast as continents and music as old as the planet itself. Earth's sleepy influence on life and climate. The wandering of continents and the breathing of volcanoes doesn't just reshape the land, it guides the very climate we live in and the evolution of life itself. Earth's geological sleep talk influences everything from ice ages to the air we breathe, all through processes so slow and gentle they're like whispers across deep time. When continents drift toward the poles, ice sheets can spread like slow-growing blankets, reflecting sunlight back to space and cooling the planet. When they cluster near the equator, dark oceans absorb more heat, and the world grows warmer. The position of Antarctica at the South Pole, ringed by ocean currents that keep it isolated and cold, is one reason our modern world has ice ages at all. Volcanoes, breathing out their gentle mix of gases, help regulate Earth's temperature over millions of years. They add carbon dioxide to the atmosphere, warming the planet, but they also trigger the weathering of rocks that slowly draws that carbon back out of the air. It's like a planetary thermostat, adjusted not by human hands but by the deep, slow breathing of the Earth itself. The drifting of continents has also guided the evolution of life in the most patient way imaginable. When land masses come together, species mix and compete. When they drift apart, populations are isolated and evolve in new directions. Australia's unique marsupials, South America's diverse wildlife, and Africa's great savannas, where early humans evolved, all were shaped by the slow wandering of their continental homes. Even the fossils we find tell stories of this ancient wandering. Identical species appear on continents, now separated by vast oceans, proof that these lands were once neighbors. The small freshwater reptile, Mesosaurus, appears in both South America and Africa, creatures that certainly never swam across the Atlantic, but lived when those continents were still snuggled together in the ancient supercontinent Gondwana. Whispers from the stone pillow. Close your eyes and imagine sleeping on a pillow made of stories, stories written not in books but in the very stones beneath your bed. Every pebble under your window, every grain of sand between your toes, every distant mountain peak visible from your bedroom is a word in Earth's longest lullaby, a song that has been humming softly for over 4 billion years, each verse lasting millions of lifetimes. Tonight, as you settle into your sheets and pull your blankets close, the planet settles too, breathing slowly with the rise and fall of continents, the gentle stretch of ocean floors, the sleepy sigh of mountains growing taller by just a whisper each year. The very bed you lie on rests upon layers of ancient dreams, limestone that once carpeted tropical seas, sandstone that remembers desert winds, shale that holds the compressed whispers of countless ancient storms. You are both dreamers now, you in your bed, Earth in its endless, patient slumber. Your dreams will last the night. Earth's dreams unfold across eons, each one so long that entire species rise and fall within a single geological thought. Yet both of you share this moment, this quiet breathing space between day and night, between one age and the next, the drowsy dance of ancient lands. In the deepest dreams, impossible things feel perfectly natural. Forests grow where ice sheets rest. Oceans lap at shores that are now mountain peaks. Deserts bloom with coral reefs. These aren't fantasies. They're memories preserved in stone, dreams that actually happened when the world was young and restless in different ways, when the continents wandered like sleepy children changing beds throughout the night. Picture Antarctica, now wrapped in its white blanket of ice 2 miles thick, dreaming of the time it wore green robes of fern and cycad. Deep beneath its frozen surface, geologists have found fossil leaves as delicate as pressed flowers in an old diary, tree stumps still rooted in ancient soil, and the preserved remains of forests that rustled in warm breezes when the continent dozed peacefully near the equator. It was part of a sleepy giant called Gondwana, then snuggled close to South America, Africa, India, and Australia in one enormous continental embrace. Even in the deepest freeze, these stone memories of summer remain, like dreams that linger after waking, the coal that burns in distant power plants, the oil that flows through pipelines, the natural gas that heats homes on winter nights. All of it is compressed sunlight from those ancient dreaming forests, energy stored in plants that photosynthesized under alien skies when the map of Earth looked nothing like tonight's bedtime story. The Sahara Desert, now an ocean of sand dunes that shift and whisper in the wind, once lay beneath actual ocean waves. Its rocks remember when sea lilies swayed in underwater currents, when trilobites scuttled across its muddy floor, when warm tropical waters stretched from Morocco to Egypt. The desert's dreaming stones still hold the shapes of ancient shells, the coiled spirals of ammonites, the delicate latte work of coral reefs that bloomed where now only mirages shimmer in the heat. High in the Himalayas, where the air grows thin and prayer flags flutter like sleepy thoughts in the mountain wind, you can find fossils of sea creatures in rocks that now scrape the belly of clouds. These tiny shells, ammonites curled like sleeping cats, brachiopods that opened and closed like sleepy eyes, marine lilies that swayed like underwater flowers, once drifted lazily in the warm, shallow waters of the Tethys Ocean. When India began its dreamy drift northward, moving slow as a growing fingernail but relentless as time itself, it carried these sleeping sea creatures on its back. The collision with Asia was so gentle, so patient, that it took millions of years to fold the ocean floor into the sky. These ancient sea dwellers never woke from their slumber. They simply rose, still dreaming of the depths, until they found themselves among the eagles and the clouds, the highest fossils on Earth, silent witnesses to the planet's most patient embrace. Stone postcards from sleepy worlds. Each fossil is like a postcard sent from one of Earth's dreams to another, messages that traveled not through the mail but through the slow dance of tectonic plates. Wish you were here, writes a delicate fern from Antarctica to its identical twin pressed into rocks in India. The weather is lovely, and we're all drifting slowly together through deep time. Alfred Wegener, the dreamy-eyed scientist who first imagined continents drifting like sleepy icebergs on a warm sea, spent years collecting these stone postcards. How else could the same sleepy reptile, Mesosaurus, have left its fossils curled up in the rocks of both South America and Africa? This little creature could no more swim across the Atlantic than a house cat could cross an ocean, unless Wegener realized there had been no ocean to cross when it lived. How else could identical seed ferns have pressed their dreamy shapes into rocks on opposite sides of the world, in India and Antarctica, in Australia and South America? These plants couldn't fly or swim. They could only drift where the wind carried their seeds, but the wind couldn't blow across thousands of miles of open ocean, unless the continents themselves had wandered, carrying their passengers from one dream to another. The fossils whispered the truth in their silent stone language. The continents had been sleepwalking for hundreds of millions of years, carrying their cargo of life from one side of the world to another. They were breadcrumbs scattered by the restless earth, a trail leading back through millions of sleepy years to show us where the wandering lands had been, and how they'd slowly, gently pulled apart. Even the tiniest passengers told the same story: microscopic plankton, preserved in layers of sediment like pressed flowers in the pages of a book, matched perfectly across oceans. Tiny freshwater amphibians that couldn't survive in salt water appeared in rocks on continents, now separated by vast seas. Every fossil, from the largest dinosaur to the smallest shell, was a thread in the larger tapestry of Earth's shifting surface, a note in the planet's longest lullaby. These discoveries were crucial in supporting Regener's dreamy theory of continental drift. Critics could deny the visual fit of the continents, could argue that South America and Africa only seemed to nestle together like puzzle pieces, but they couldn't explain how a freshwater reptile had managed to swim across the Atlantic, or why the same delicate fern had grown in both the warmth of India and the ancient tropics of Antarctica. The fossils carried the truth of tectonics in their silent testimony, proving that the solid ground beneath our feet had been on the longest, slowest journey in Earth's history. Islands born from fire dreams. Far out in the deepest blue of Earth's sleepy oceans, where the water rocks itself to sleep with gentle swells, and the nearest land is just a memory on the horizon, islands rise like dreams made solid. These aren't the violent births you might imagine, explosive eruptions that shatter the peace of the sea. Instead, they're slow emergences, volcanic lullabies sung from the Earth's warm heart, melodies that take millions of years to complete. The Hawaiian Islands are Earth's sleepiest story, a tale written in lava and coral across the middle of the Pacific. Each island is a chapter in a dream that began over 80 million years ago, when the Pacific plate started its slow drift over a single patient flame deep below, a hot spot that burns as steadily as a pilot light, never moving, never dimming, just waiting. Picture this vast plate drifting like a sleeping whale over that stationary plume of heat. As it moves, volcanoes bloom and fade like flowers in a time-lapse dream. The big island of Hawaii still glows with fresh lava, its young volcanoes breathing fire into the cool ocean air, building new land with each gentle breath. Steam rises where lava meets water, like the earth sighing in its sleep. To the northwest, Maui and Oahu have grown quiet with age, their volcanic fires long extinguished, their peaks softened by millions of tropical rains, their slopes clothed in green rainforests and gentle waterfalls. Kauai, the Garden Isle, has slept so long that erosion has carved deep valleys into its volcanic bones, creating a landscape of impossible beauty, emerald cliffs that drop into sapphire seas, waterfalls that fall like silver threads through morning mist. Beyond them, hidden beneath the waves like sunken dreams, lie the Emperor Sea Mounts, a chain of drowned mountains that trace the Pacific Plate's journey back through eons. These sleeping giants once stood tall as islands, once hosted their own coral reefs and tropical birds, but time and the slow settling of the seafloor have pulled them beneath the waves. They remain as stepping stones in the ocean's memory, invisible but not forgotten. Even the bend in the Hawaiian Emperor chain tells a sleepy story. The moment 50 million years ago, when the Pacific Plate rolled over in its sleep and chose a different direction, like a dreamer shifting positions in bed. That kink in the chain isn't just a geological curiosity. It's a timestamp of Earth's shifting dreams, a frozen record of when an entire ocean floor reorganized its longest journey. Iceland sits where fire meets ice, where a hotspot rises to meet the mid-Atlantic ridge in a rare geological embrace. It's like sleeping next to a warm fireplace while snow falls outside, a cozy contradiction that creates a land of geysers and glaciers, hot springs and aurora, where the Earth's warm breath steams through cracks in winter ice. The island grows wider each year as the ridge spreads, pulling Europe and North America apart, grain by grain, breath by breath. The Galapagos Islands drift slowly eastward on the Nazca Plate like a chain of sleeping turtles, each island a different age, a different chapter in the same volcanic dream. The youngest still smoke with fresh lava, the oldest have become gardens of evolution, where finches learned to sing different songs and tortoises grew different shells, each island dreaming its own version of life. Myths of the Sleepy Giant. Before seismographs could listen to Earth's heartbeat and satellite maps could trace the drift of continents, when the ground shook unexpectedly or mountains breathed fire into the night sky, people told sleepy stories to explain their restless world. These weren't just explanations, they were lullabies for frightened souls, ways to make sense of a planet that sometimes tossed and turned in its ancient slumber. In Japan, where the islands rest uneasily above the meeting of four tectonic plates, earthquakes came from Namazu, a giant catfish longer than the entire archipelago, dreaming in the deep mud beneath the seafloor. Most nights, the god Kashima held it still with a great stone, like a parent's gentle hand on a restless child's forehead. But sometimes Kashima's attention wandered, his grip relaxed, and the great fish would turn over in its sleep, its dreams of swimming sending tremors through the islands above. The ancient Greeks, living in a land where the African plate slowly grinds beneath Europe, imagined Poseidon with his mighty trident, stirring the earth like a dreamer tossing restlessly in bed. Each earthquake was a divine message, they thought, a god's way of communicating across the vast distance between heaven and earth. Mount Etna, they said, was Hephaestus's workshop, where the god of fire and metalworking crafted weapons for the other gods. The mountain's rumbles were just the sound of divine hammers on immortal anvils, echoing up from the sleepy forge far below. In Polynesia, where islands rise from hotspots like dreams made manifest, Pele the fire goddess shaped the land with her restless energy and creative dreams. Each eruption was a new thought taking form, each lava flow a stroke of divine artistry. The Polynesian peoples honored her with chants and offerings, understanding that they lived on land literally dreamed into existence. Volcanic thoughts cooled into solid ground. The Norse, surrounded by the slow grinding of European geology, told of Loki bound beneath the earth, the trickster god whose punishment was to lie chained in darkness, while venom from a great serpent dripped onto his face. When the poison burned, Loki would writhe and struggle, and his movements would shake Midgard, the world of humans. Even in this myth of punishment, there was recognition that something vast and powerful stirred beneath the ground, something that dreamed restless dreams of freedom. In the Andes, where the Nazca Plate still slides beneath South America, the Inca spoke of Pachamama, the Earth Mother, whose breathing caused the mountains to rise and fall. When she was content, the earth was still. When she grew restless, the ground would shake and the volcanoes would glow like warm embers in a sleeping hearth. The mountain peoples understood that they lived on the body of a sleeping giant, and they treated the earth with the reverence due to something alive and dreaming. These stories weren't primitive ignorance. They were humanity's first sleepy acknowledgement that the earth was alive, that it dreamed its own vast dreams, that it turned restlessly in a slumber so deep and slow that entire civilizations could rise and fall between one movement and the next. The myths gave faces and names to forces too large and slow to comprehend, turning terror into story, uncertainty into a kind of bedtime tale that helped people sleep peacefully on a planet that never quite held still. Listening to Earth's sleepy heartbeat. Today, we have gentle instruments that rest on the ground like stethoscopes, listening to the Earth's dreams with electronic ears more sensitive than any human could be. Seismographs sit in quiet stations around the world, recording every sleepy sigh, every restless turn of the tectonic plates, every small adjustment the planet makes in its billions-year slumber. These vibrations travel through the earth like dreams moving through a sleeping mind, bending and changing as they pass through different layers of rock and metal. Just as dreams take on different qualities as they move from the conscious to the unconscious mind, seismic waves speed up in hard rock, slow down in soft sediment, and bend when they encounter boundaries between different materials. By listening carefully to these underground whispers, Scientists can map what lies hidden beneath our feet, where slabs of oceanic crust sink sleepily into the warm mantle like heavy blankets, settling into a soft bed where hot plumes rise like warm air from a heater. Even what the Earth's iron heart looks like as it spins slowly in the dark, 4,000 miles below the surface. GPS satellites orbit overhead like caring parents watching over a sleeping child, measuring how the continents drift in their geological sleep. The movement is incredibly slow, just a few centimeters each year, about as fast as your fingernails grow. But the satellites are patient watchers, accumulating data year after year, decade after decade. In California, they record the Pacific Plate sliding northward past North America like a sleeper slowly pulling up blankets. In the Himalayas, they measure India still pressing gently into Asia, pushing the mountains higher grain by grain, breath by breath. From space, other satellites peer down with radar eyes that can detect the tiniest changes in the Earth's surface. They watch how the ground swells and settles after earthquakes, rising and falling like a sleeper's chest. They can measure changes as small as a few centimeters, the Earth's equivalent of a gentle sigh in sleep, invisible to us but clear to their electronic vision. Deep in the oceans, where most of the planet's tectonic dreams unfold far from human eyes, robots and submersibles descend like mechanical lullabies into the abyss. They explore hydrothermal vents along mid-ocean ridges, where new seafloor is born in clouds of mineral-rich water heated by the Earth's warm heart. These underwater gardens bloom with life that has never seen sunlight, creatures that feed on the planet's chemical dreams, tube worms and bacteria, and ghostly crabs that live in the Earth's deepest thoughts. The ocean floor spreads so slowly that you could sit beside a mid-ocean ridge for your entire lifetime and never see it move. Yet the robots faithfully record this slowest of motions, this gentlest of births, as new rock emerges from the planet's depths, like thoughts becoming conscious, cooling from liquid fire into solid stone, then slowly drifting away like memories moving from recent to distant. Tomorrow's sleepy geography. The continents are still wandering in their geological sleep, and their dreams will reshape tomorrow's world in ways both gentle and profound. Africa drifts northward like a sleepy giant slowly rolling toward Europe, closing the Mediterranean Sea drop by drop, year by year. This ancient sea, which has witnessed the rise and fall of countless civilizations, will eventually become just a memory locked in stone. In 50 million years, just a comfortable nap in Earth's timeline. Africa will embrace Europe completely, folding the Mediterranean into a memory and raising new mountains where waves once lapped at Italian shores. Rome and Athens, if any trace of them remains, will find themselves at the foot of peaks as tall as the Himalayas, ranges that don't yet exist but are already dreaming themselves into being in the slow collision of continents. The Atlantic Ocean, which has been stretching and yawning wider since Pangaea broke apart 200 million years ago, may eventually grow tired of expansion and begin to close again, like a sleeper who has stretched too far and now curls back into a comfortable position. The Americas might drift slowly back toward Europe and Africa, like children unconsciously seeking the warmth of parents in sleep, eventually forming a new supercontinent, perhaps Pangaea Ultima, the next great gathering of Earth's scattered dreams. Imagine that future world, hundreds of millions of years from now, all the familiar continents snuggled together again under one vast blanket of land, surrounded by a single sleepy ocean. The climate would shift like seasons in a very long year, with vast interior deserts where no ocean breeze could bring relief, and narrow coastal belts where all the planet's life would cluster like creatures gathered around a campfire. Other models suggest different dreams for the distant future. Perhaps all the continents will drift northward toward the Arctic, creating a supercontinent called Amasia at the top of the world, where the aurora borealis dances over lands we can't yet imagine. Or maybe they'll reunite across the Pacific, forming Novo Pangaea as Asia and the Americas embrace across the shrinking ocean. The details remain uncertain, but the theme is clear. The map will change. The continents will not remain where they are, and Earth will continue its restless cycle of gathering and breaking apart, like a dreamer who can never quite find the perfect sleeping position. In East Africa, the Great Rift Valley widens year by year, like a sleeper slowly stretching in bed. One day, seawater will flood in from the Red Sea and the Indian Ocean, creating a new sea between Somalia and the rest of Africa. Madagascar will drift further east, perhaps eventually colliding with India like two sleepy continents sharing the same dream. New islands will rise along the rift's margins. Just as Iceland straddles the mid-Atlantic ridge today, each one a volcanic thought made manifest. The Himalayas will continue to grow, though so slowly that 1,000 human generations will pass before they gain the height of a single skyscraper. These youngest and tallest mountains on Earth are still children by geological standards, still pushing upward as India continues its ancient collision with Asia, still dreaming of heights we can barely imagine. The patience of stone. What makes Earth's story so wonderfully sleepy is its profound patience. A patience so deep that it makes human time feel like the flutter of a moth's wing against a mountain. While we measure our lives in decades and our civilizations in centuries, the Earth measures its dreams in millions and billions of years, each geological thought lasting longer than the entire history of life on land. The Himalayas are still growing, still rising as India continues its sleepy collision with Asia. Each year they gain a few millimeters, about as fast as your fingernails grow, so slow that if you lived for 1,000 years, you might not notice the change. Yet those tiny increments, added up across the vast span of geological time, have lifted fossil seafloors to heights where only clouds and eagles can visit, where the air grows so thin that every breath becomes precious. The Atlantic Ocean spreads at the same dreamy pace, its seafloor pulling apart grain by grain, year by year. If you could live for millions of years and watch from space, you might see the ocean breathing like a sleeping chest, inhaling and exhaling across eons. Yet this whisper-quiet motion has opened an entire ocean where once there was solid land, carrying continents thousands of miles from where they started their journey. Even the fastest geological processes move with the patience of a master gardener. When Mount St. Helens erupted in 1980, it seemed catastrophically sudden to human observers. Yet the mountain had been preparing for that moment for thousands of years, slowly gathering pressure, slowly warping and bulging, sending tiny signals that geologists were only just learning to read. The eruption itself, violent as it appeared, was just a moment's release in a process that will take centuries to complete as the mountain rebuilds itself from its own debris. Mountains rise like flowers blooming in extreme slow motion, imperceptible moment by moment, but magnificent across time. The Rockies, the Alps, the Andes, all of them are still growing, still reaching toward the sky like sleeping giants slowly stretching after a long rest. Some peaks gain height while others are worn down by wind and rain and ice, but the process continues with the patience of stone, each change so small that only the most sensitive instruments can detect it. Volcanoes breathe with the rhythm of the very slow, their hearts beating in cycles measured in decades or centuries rather than seconds. Between eruptions, they sleep so deeply that forests grow on their slopes, cities nestle in their shadows, and people forget that they live beside sleeping giants. Yet even in sleep, the volcanoes dream, their magma chambers slowly refilling, their internal pressures slowly building, their rocky hearts beating with a rhythm older than any human memory. A lullaby written in stone. There's something deeply comforting about Earth's sleepy rhythms, something that speaks to the part of us that seeks peace in an uncertain world. While human civilizations rise and fall like dreams within dreams, flickering in and out of existence like candle flames in a vast cathedral, The planet continues its patient work, providing a stable stage for life's brief but beautiful performances. Empires that once seemed eternal, Egyptian dynasties, Roman legions, Chinese kingdoms, crumble to dust faster than mountains can grow an inch. Languages are born, flourish, and fade to silence while ocean floors spread just a few miles. The pyramids of Giza, ancient beyond human memory, have watched the Nile Delta grow by mere meters since they were built. In geological terms, they were constructed yesterday. In human terms, they are monuments to eternity. We are like mayflies dreaming. We live on a sleeping whale, our entire species just a brief flutter in Earth's long night. Homo sapiens has existed for perhaps 300,000 years, barely a moment in the 4.5 billion-year story of our planet. All of human history, from the first cave paintings to the space program, from the invention of agriculture to the internet age, has unfolded while the continents have drifted less than the length of a football field. Yet we're fortunate to be conscious passengers on this dreamy journey, aware enough to read the story written in stone, to understand that the ground beneath us has travelled incredible distances to arrive at this moment. We can trace the path of our wandering continents, follow the fossil breadcrumbs left by drifting lands, and even measure the continuation of their journey with instruments more precise than any ancient dreamer could have imagined. Tonight, as you close your eyes and settle into sleep, remember that your bedroom rests on rock that has travelled thousands of miles to be here. The limestone beneath your foundation may have formed in a tropical sea near the equator. The granite in your countertops might have crystallized deep in the roots of mountains that have long since worn away. The sand in your garden could have been desert dunes or beach or river bottom before the slow dance of tectonics carried it to its present home. You and the earth are both dreamers now, both travelers through time. You dream the quick dreams of consciousness, stories that unfold in hours, emotions that change like weather, thoughts that flash like lightning across the landscape of your mind. Earth dreams the slow dreams of geology, stories that unfold across eons, emotions measured in ice ages and warming periods, thoughts that move like glaciers across the continents of time. Your dreams will fade with morning, but Earth's dreams will continue for billions of years to come, slowly reshaping the world, slowly writing new chapters in the longest story ever told. Mountains will rise where oceans now roll, seas will spread where deserts now stretch, and continents will wander to new destinations carrying passengers we cannot yet imagine. Rest well on this ancient wandering world. Let the slow rhythm of tectonic drift carry you into your own peaceful sleep, knowing that you're part of something vast and patient and beautiful. The planet dreams of new mountains and different seas, while you dream whatever dreams come to sleeping minds. Both of you carried forward through the night by forces older than memory, deeper than thought, and more gentle than the softest lullaby. Sweet dreams, fellow wanderer, on this sleepy, ever-changing world. The earth will keep you safe as it has kept countless dreamers before you, moving so slowly and carefully through space and time that you'll never feel its motion, only its endless, loving patience. Sleep now, knowing that you rest on a world that has been dreaming for longer than the oldest stars and will continue dreaming long after all the stars we know have grown old and dim. The earth's eternal slumber, the world is dreaming beneath you, breathing with the rhythm of ages, its heart beating in the slow percussion of tectonic movement. Every tremor is a sleepy adjustment, every volcanic eruption a brief moment of sleep-talking in the planet's endless rest. You are safe in this vast dream, cradled by forces that have been gentle for billions of years, that will continue to be gentle for billions more. Dream with the earth tonight. Let your quick, bright dreams dance with its slow, patient ones. Let your restless sleep be soothed by its deep, eternal slumber. Tomorrow will bring new wonders, but tonight there is only this, you and the planet, both dreaming, both traveling through time at your own perfect pace, both part of the same long, beautiful story that began with fire and will end with wisdom. The earth dreams, and in its dreams it carries us all, every sleeper, every dreamer, every soul that has ever rested on its patient surface. Sleep well, and let the planet's ancient lullaby carry you through the night and into whatever dreams await, knowing that you are held by something larger and more loving than you can imagine, something that has been dreaming of moments just like this for longer than time itself.